Okay. Good evening. Good evening. Can you hear me? Good evening.
Good evening, sir. Yes, sir. Audible.
Now, before everybody get settled down, we'll do a small question. And then we'll start today's topic. The stability factor S is given as S equal to change in IC by change in IC naught. Calculate this factor for different circuits. Now this problem, this stability factor I have not done because these kind of questions of late you cannot expect in GATE exam, right? Questions like this you can expect in IES exam. But these are from old textbooks, right? Now what is this S? S is given as change in IC by change in IC naught. We know that IC is beta IB plus some leakage current beta plus 1 times of IC naught. But because we don't know IC naught, till now we don't know, we have not introduced IC naught, leakage current and all that. So we want to avoid this. Instead, what if I differentiate IC with IC naught now? Change in IC by change in IC naught. What will you get? Differentiate the whole equation with respect to IC naught, or differentiate with respect to IB, what you will get? Change in IC, differentiate with respect to IC or IB. Differentiate with respect to IC, what do you get? 1 equal to beta into change in IB by change in IC plus beta plus 1 times of change in IC naught by change in IC. From here, change in IC by change in IC naught equal to, what do you get? Change in IC by change in IC naught. 1 plus beta by 1 minus beta into change in IB by change in IC. So because we don't know this IC naught, in order to skip that, I differentiated here with respect to IC. So I got some equation. So in any circuit, in any DC circuit, biasing circuit, if you get a relation between IC and IB, then you can solve this problem, stability factor. It's not a big thing. You have to get a relationship only between IB and IC, right? 1 plus beta by 1 minus beta into change in IB by change in IC. So this is the factor S. Now this factor you can calculate for all the biasing circuits. For example, fixed bias. Now, when do you say that a circuit is stable? If IC depends on IB, then that is a worst circuit. But if your IB depends on IC, then there is some sort of negative feedback. Feedback means what? It is not that output depends on input. It is that the input should also depend on the output. So that will happen only when there is an emitter resistor. When there is no emitter resistor, there is no negative feedback. Then the stability is very poor. That we can see here in the first equation. We know that IB is VCC minus VB by RB. And IC is beta times of IB, or beta times of VCC minus VB by RB. So this is something we have already seen, is it not? Now, what is change in IC by change in IB? If you differentiate IC with respect to what? Change in IC by change in IB. This equation tells that here, change in IB by change in IC. Now this equation does not have any IC at all. IC is constant. IC is constant. So therefore, the stability factor S equal to 1 plus beta by 1 minus beta into 0. So now you can see here, your IC is purely dependent on what? Beta, is it not? It's purely dependent on VCC, VB, and your IB is constant. This is the worst circuit. IB is constant. But what is our aim? Our aim is to see that IB should depend on IC and IC should depend on IB, both. But here IB is constant. So 1 plus beta by 1 minus beta, 1 plus beta. So this is the worst case. Worst case. Then what will be the best case? The best case, this is the worst case. Best case is going to be 1. Best case is your S should be equal to 1. So we have to try for 1, right? Let's see what happens if I put an emitter resistor. If I put an emitter resistor, then this is IE. IE can be written as IC plus IB. So if you apply KVL at this loop, KVL, the second circuit, then VCC equal to IBRB plus VB plus ICRE plus IBRE. Now we want change in IB by change in IC. So we'll bring IB to the left side. IB into RB plus RE is equal to VCC minus VB minus ICRE. So what is IB? It is VCC minus VB by RB plus RE. Such type of questions will never come, right, in GATE exam. Some students, they are repeatedly asking, sir, we want to derive this and all. For them, it is RE by RB plus RE into IC. See, what is that? Simple mathematics. You got a relationship between IB and IC. Now you have to differentiate change in IB by change in IC. It is minus RE by RB plus RE. Then what is S? S equal to 1 plus beta by 1 minus beta times of change in IB by change in IC, minus RE by RB plus RE. Now this we already know. If I want S equal to 1, then my RB or RE should be much, much greater than RB. If my RE is far greater than RB, you can just neglect RB here. Then your RE will get cancelled, minus of minus plus, your S will be equal to 1. So this is something we have already done, is it not? Your RE should be far greater than RB by beta plus 1. We have already done that for beta stabilization, is it not? So like that, you can calculate for different biasing schemes. What is there? You have to get a relationship between IB left side you have to bring, IC right side, then you differentiate, substitute, that's all. Are you getting? So these are all time pass, happily have a cup of coffee, write one KVL, bring IB left side, IC right side, differentiate. Are you getting? So all these are exercises, basic calculus exercises. Are you getting? What is this circuit? This circuit is equal to VCC R2 by R1 plus R2, V Thevenin in series with R Thevenin, which is R1 parallel with R2. Here you have the BJT. You have VB here. And this is IE. IE means IC plus IB, RE. Again, you have to write KVL, right? Minus VTH plus IB into RTH plus VB plus IC into RE plus IB into RE equal to 0. All right. Then what we have to do? Bring all IB left side. Then what you will get? See here, in the previous equation, what is here? In the place of RB, what do you have in the place of RB? From previous diagram, circuit, you realize that your RTH is nothing but RB, the previous diagram. Yes or no? So RTH, your VTH is VCC. So what is S? S is 1 plus beta by 1 minus beta into change in IB by change in IC. This is minus RE by RE plus RTH you will get. RTH. So when S will be 1? S is 1 only when RE is far greater than RTH. So what is RTH here? RE is far greater than R1 R2 by R1 plus R2. So like that you can do. In IES, once for 10 marks they have given this. Same thing only. Instead of NPN, they have given a PNP circuit. RE, RB. And please always apply KVL at what loop? Input loop. These are all dependent sources. So your output current will always depend at the input side. So in all BJT circuit or MOSFET circuit, DC circuits, always you should focus at the input loop. If you go at output loop, then you will have two unknowns. Current will be an unknown, VCE will also be an unknown. Always remember, whenever you are doing BJT circuits, you should always focus on the input loop. Always input loop, right? Because these are dependent sources. The output is dependent on the input. So this is IB. This is IC plus IB. So what is V? The voltage V with respect to ground is ICRE plus IBRE plus VEB plus IBRE. So IB left side, IC right side, RB plus RE. So again, same thing we got. IB is V minus VEB by RB plus RE minus RE by RB plus RE into IC. So change in IB by change in IC. It is minus RE by RB plus RE. Okay, this is enough, is it not? I don't think I'm paid for this, right? So change in IB by change in IC. So what is S? It is 1 plus beta by 1 minus beta into this factor minus RE by RB plus RE. So if you want S1, good stability, your RE should be far greater than RB by beta plus 1 or RB. Okay. So like that, you can calculate stability factor. In fact, if you ask me, first equation, right? First equation, if you see, there is VB, there is RB also. So you can differentiate with respect to VB, you can differentiate with respect to VCC. I mean, stability can be found with respect to any case, right? So have you observed in all these cases, what are we getting? 1 plus beta by 1 minus beta into emitter resistor by emitter resistor plus base resistance. In every case, this is the same similar thing, right? Emitter resistor by emitter resistor plus base resistance is that factor we are getting. So by seeing a circuit, we can tell this is RE, this is RB. So what you will get? 1 plus beta by 1 minus beta into R minus RE by RB plus RE, right? Emitter resistance by emitter resistance plus base resistance. You don't have to do even this, right? So for every case, this is what we are getting. Okay. Shall we start today's topic? Yeah. Good evening, everyone. Good evening. You can take a screenshot of this, right? Okay. So today's topic is current mirror. So this week we will complete the syllabus, right? This week we are going to complete the syllabus. From next week, actually I should have done it 10 days before. If the classes were from 2 to 8, it seems for other lecturers you have agreed for 2 to 8, but I don't know why you have not agreed for me, right? So because 3.5 hours a day or 3 hours hardly, it takes almost 20-25 days, is it not? But instead, if we would have done from 2 to 8, then in 2 weeks we would have completed. Anyways, so after a current mirror topic, BJT, MOSFET, diode, op-amp, everything we have completed, right? Now we have some miscellaneous. What is the miscellaneous we are left with is, we have to do some Zener circuits, right? Voltage regulators. Some Zener basic problems also we will do. And we are left with non-idealities in op-amp. Non-idealities. Like input offset voltage calculations, current, the errors we have to calculate, slew rate, CMRR, and so on, right? That is the second part. So Zener circuits are there, non-idealities in op-amp, and oscillators, sinusoidal oscillators, we have to do, feedback amplifiers. So with that, we will close the syllabus, right? Acha, Harsha is telling from 2 to 4 you have a maths class also every day. Okay then that is fine. So current mirror, in a current mirror, the collector current depends on base current and the collector current should be independent of collector to emitter voltage. So what do you mean by that? It means that IC is proportional to IB and IC is independent of VC. So this is a definition of active region. If somebody asks you, when is a transistor in active region? What will you say? IC should depend on IB and IC should be independent of VCE. That means all the transistors should be in active region, right? Of course, in analog, BJT circuits are all in active region, right? Now, and moreover, in current mirror circuits, mostly all transistors should be alike because they are on an integrated circuits. So transistors in current mirror are usually matched transistor pairs. So unless and until I mention, you have to consider that all transistors are exactly same. It is more convenient for designer to have a matched pairs because transistors are fabricated on layers, metal on one layer, diffusion on one layer, right? So it's much easier for them to have transistors which are exactly same, right? So let us have the basic current mirror. This basic current mirror is given by one of the best analog designers the world has ever seen, right? His name is Widlar. He's an analog genius. This guy has given the basic current mirror, and this design detail is found just about every analog IC. You take any analog IC, you will find, at least 20, 30 current mirrors like that. And the basic current mirror is this. The basic idea is this. He has given, right? So this is I copy. Here you have a reference current, I reference. Q1 and Q2. Now, the I copy is going to follow I reference, and let us consider both transistors are same, right? Similar. Now, what is the relationship between I copy and I reference? So let us go step by step here. Suppose I take here IC. All right? If this is IC, then what is the base current here? It is going to be IC by beta. The base current is going to be IC by beta. you can see that Q1 and Q2 transistors both have the same VB. Can you see? Both have the same base potential, same emitter potential. So when both are same and they are similar, if this is IC by beta, this should also draw IC by beta. IC by beta, IC by beta. Then what is the total current here? 2 IC by beta. 2 IC by beta. If the base current is IC by beta, then the collector current is IC. The collector current is IC. Okay. So we'll go once again, step by step. Tell me which is the first step. This is the first step I started. IC. First step is IC. Second step is IC by beta. Third step is IC by beta. Fourth step, entering is leaving, is this. And if IC by beta is base current, I copy is IC. Fifth step. Last sixth step is I reference. What is I reference? I reference equal to summation IC plus 2 IC by beta. It is equal to IC into 1 plus 2 by beta. Am I right? But what is IC? IC is nothing but I copy. I reference equal to I copy into 1 plus 2 by beta. Or I copy equal to I reference by 1 plus 2 by beta. Am I right? So, do you think I copy and I reference both are same? No, there is a slight error here. The error is so this week we are going to complete and session will be same. Don't worry, because we are used to this, right? So we will have from the same timings we will have. I'm just saying because I don't know that you have maths class and some of the students are going to college also, right? They have college classes also they have to attend. So in spite of that, they are attending classes. So I really appreciate them. Your college work is also there, burden, right? Some of you are in third year also, right? Okay. So now what is the disadvantage in this? Disadvantage. For beta equal to 100, there is a current error of 2%. For beta equal to 100, 2 by beta, 0.02, there is a current error of 2%, right? That is the one. 2% in analog is very huge. You might think what is there in 2? No, it's unacceptable, right? 2% is huge. Next, another disadvantage is, now what happens if I connect some load here, and keep changing the load? If load changes, then VC changes. VC changes. This in turn will change IC. This is called early effect. Early effect. So your IC is now dependent on VC also, right? Your IC should be independent of VC, ideally. Ideally, it should be independent. But a practical BJT, what can we do? If load changes, VC will change. If VC changes, your IC will change. So there will be early effect also, right? The current error of 2% is there. Apart from that, there is also early effect. So two things we have to decrease, right? Now, first of all, what is this connection here? What is this connection? Huh? Why are we connecting it like this? Q1. What do you mean by this? What do you mean by this? Q1 transistor acts as a diode. Q1 transistor acts as a diode. So a diode should look like this, right? This is a diode. Huh? Suppose if you give 5 volt, so if this is 5 volt, 1K, 3 diodes are there, 0.7, 0.7, 0.7. How much voltage will be dropped here? 2.1. Current I equal to 5 minus 2.1 by 1K. It is 2.9 milli. Am I right? Now, if suppose a designer comes to you and says that he wants this circuit on an IC, on an integrated circuit, how will you build diodes? Because on an IC, I told you, it is either BJT or MOSFET, right? So how will you build such a structure on an integrated circuit? To build such a structure, we have to connect transistors like this. Am I right? Now, if collector base terminal is shorted, then the collector base junction is reverse bias. If the collector base junction is reverse bias, BJT will happily be in active region, provided you forward bias the base emitter junction. And see how clever Widlar is, right? With a single shot here, he said, I am biasing the BJT. Now, biasing with a voltage divider was such a big headache. Base emitter junction should be forward bias. Collector base junction should be reverse bias. Have you seen a self bias circuit here? See here. In self bias, this potential should forward bias this diode, and there should be enough headroom for collector base junction also to get reverse bias. So accordingly, we have to choose the values of R1 and R2. So, but Widlar, what he did, he said, if you want to reverse bias this, I will short, right? So reverse bias. Forward bias, I will give a voltage here. If you give a voltage, automatically this diode is on. No? This diode is on. So this is a simple way of biasing a transistor. So from a voltage divider bias, Widlar came with an idea that you connect a wire like this, right? From base to collector, biasing is over for BJT, right? Sir, I want a BJT to be biased. Biasing means base emitter junction should be forward, collector base junction to be reversed. What he did, one wire he connected from base to collector. Finished, the transistor is on. Base emitter junction is on, collector base junction is reverse bias with that short. BJT is happy in active region. At the same time, it is now behaving like a diode. Can you see? There is 0.7 volts here. There is 0.7 here. There is 0.7. So this circuit is as if there are, see, there is a short from here to here, short, and a diode, short, diode, short, diode. So this circuit and this circuit both are same. Am I right? Both are same. So here again you are going to have 2.1 volt. The current is 5 minus 2.1 by 1K. It is going to be 2.9 milliampere. So what is the best way to make diodes? Is to short the base and collector junction. Are you getting? Okay. Then what is this basic current mirror? The basic current mirror is a diode connected to transistor. Diode connected to transistor. So now you might say, what happens if I connect a diode to a transistor? I am having a diode. This is Q1. And I am connected it to a transistor. What will happen? I told you in my diode, during the introduction of diode, I told you that a diode and a transistor, they have almost like the same characteristics, but it all depends on the cause and the effect. Cause and the effect. A diode is basically a logarithmic device. A logarithmic device. A BJT is basically an exponential device. An exponential. So what happens if I connect log to exponential? If I connect log to exponential, then the nonlinearity is highly nonlinear circuit. By cancelling the nonlinearity, I am going to have a linear relationship between the input I reference to I copy. How is this possible? If the current changes the voltage, then it is log. If the voltage changes the current, it is exponential, right? So I reference is the input. So who is the input to the current mirror? You can see here, the current mirror here. See here, who is the input? I reference leads to VB1. This is VB1. I reference leads to VB1. VB1 equal to VB2. VB1 is equal to VB2. VB2 leads to I copy. So this is something like this. If you don't have Q1 transistor, how Q2 will be on? Q2 is on if you supply VB. If you supply VB, then Q2 is on. Then Widlar thought, okay, a transistor should be biased. He needs VB2. Can I get VB2 without a voltage divider with VB1? So he wants to supply VB2 with VB1. But from where did you get VB1? He will connect a diode here. He will connect a diode. See here, let me draw it like this first. This is Q1 transistor. These two terminals are shorted. Two terminals, right? Suppose this is 10 volt. This is 5K. What is the current here? I reference. So this voltage is I reference equal to 10 minus 0.7 by 5K. 10 minus 0.7 by 5K. We have done some problems. Somebody told me in the comment section that this is around 1.86, if I remember, right? When we were doing the calculations. Maybe I'm right? So don't worry about the number. 1.86 milliampere for 5K. So if you see the characteristics of the diode here, VB here, VB1, and I reference or IC. IC or I reference both are almost same. So you are steering a current of 1.86 and it develops a voltage. So I reference is the input. It develops a voltage of 0.7 or let it be 0.7001 or 701. Even if you put 0.701, it is almost 1.86 only. It is 0.701. Now what Widlar did, okay, I have a transistor with 5K, I got 0.701. This he will give it to one more BJT here. One more BJT which needs biasing. No voltage divider, nothing. But this BJT and this BJT both are same. Now naturally you will get 0.701 here, 0.701. And once the BJT is on from the supply, from the VCC supply, you are going to get a current of 1.86 milliampere because Q1 characteristics and Q2 characteristics are same, 0.701, 1.86. Now let us play a trick. What if I change this 5K to 1K? I'm changing this 5K to 1K. I'm changing. So 10 minus 0.7 by 1K, 9.3 milli. This is going to be 9.3 milli now. 9.3 milli. But at 9.3, please, this voltage will not be 0.701. It will be 0.702. It is not going to be 0.701. It is going to be 0.702. So once I shift to 1K, this has become 0.702. Nicely, this 0.702 is applied here. When it is applied here, this potential, now this voltage is changed here, 0.702. Now this current is going to be 9.3. This is called a mirror. Mirror means what? It's reflection. Whatever happens at Q1, the same thing will happen at Q2. Now we are asking differential amplifier or whatever amplifier, we are asking, boss, how much current you want? Here, this I'm having a differential amplifier. And this differential amplifier needs a constant current of say 9.3 milliampere. 9.3. What will I do? I will connect a BJT here, and this BJT, I am going to put a resistor here, and I am going to steer 9.3 from here. Finished. 9.3 milliampere will flow the differential amplifier. It will split into two parts. Happy, is it not? So with a diode, I am able to control the differential amplifier current. In fact, if you connect one more in parallel here, one more differential amplifier will work here. One more in parallel if you connect, one more amplifier. So one diode is enough to bias 1,000 amplifiers. 1,000 amplifiers you will connect in parallel. At the corner, one diode will be on. The moment that diode is on, 0.7 will come. Takka, 0.7, you will give it to all transistors. Every transistor is on. Otherwise, to give 0.7, what stunt we were doing? We nicely put one voltage divider, we got 4. Then we thought, array, he needs 0.7, I gave 4. Then extra resistor we are putting for 3.3 drop. So left side resistor, right side resistor, up resistor, down resistor. What for? To give 0.7. But Vidlar idea is what? You need 0.7, I will give 0.7. That's all. That 0.7, I am giving it from a other BJT. A transistor will bias another transistor. That is the technology. Are you getting? Transistor biasing with resistors is an outdated concept. Is it? In fact, it is waste. Voltage divider bias and all that. I still remember when I was studying electronics, there is a bit, I still remember in a bit, which is the universal bias. I used to write voltage divider bias is universal. Now that biasing itself, where is it universal? That biasing circuit is in the museum now. Are you getting? We have to put such, because you don't get practically those circuits on a wafer. Only outdated things, what we will do? Old things, right? Old Stone Age things. Antique pieces will be there, no? So such things should be sent to museum. So voltage divider bias, all these old circuits, we have to send it to the museum. Current mirrors, differential amplifier pairs, level shifters. These are the technology we are running, right? Okay. So now tell me, who should bias a transistor? A transistor should bias another transistor. Who should act like a resistor? A transistor should act like a resistor. A transistor will act like a resistor in a current mirror. A transistor will act like a diode if base and collector are shorted. A transistor will act like a capacitor in a level shifter. A transistor will act like a transistor, of course, in any amplifier. Transistor should act like resistor, transistor should act like capacitor, transistor should act like diode, transistor, of course, should act like a transistor. So, one army of transistors will be there. It's like ants. Yeah, you have seen ants, right? I mean, you would have studied in your younger classes about ants. There are few ants which are doing a specific job, right? They are social workers. There are few security guards. There are few, right? There's king and the queen and a lot of stuff. So similarly, you might find transistors everywhere, but the job they are doing are different. Some are doing the job of resistors, some are doing the job of capacitors, some are doing the job. Are you getting? And the packaging is very small. Even in a small space, you can fabricate them, right? So who is acting as whom now? Q1 acts as a diode. What is the input to a diode? What is the input to a diode? I told you. How did you start? We will connect a resistor. I reference leads to VB1. The drop. Whenever a current flows through a diode, it gives a drop. But VB1 is same as VB2. Because VB2 you are supplying for Q2, the base emitter junction is forward bias. Now, Q2 base emitter junction is forward bias. Once it is forward bias, VB2 leads to what? I copy. So the mirror, exactly, I copy is going to act like I reference. But of course, small error is there, 2 by beta. This error we can eliminate in future, right? That is why I like this equation. I want to write like this. See here, this is Q1, this Q2. If beta is large, I would like to write equations like this. Suppose this is IC2 and this is IC1, and if beta is large, it's almost IC1, right? So I would prefer writing this as IC2 equal to IS into e power VB2 by VT. VB2 by VT, right? Your IC is because of VB2, but VB2 equal to VB1. VB2 equal to VB1. Therefore, what should I write? Your IC2 is dependent on VB1 by VT. But VB1 is an output. VB1 is an output. Who is input here? IC1 is input. So, ICS into e power VB is, what is VB? IC is IS into e power VB by VT. No? What is VB? VB equal to VT log IC by IS. So what should I write now? In the place of VB, I will write VT log IC1 by IS. Can you see? So what is happening now? What is happening? VT gets cancelled. Exponential log cancelled. The non-linearity gets cancelled. IS gets cancelled. IC2 is almost IC1. This equation I like, because when I look at this equation, you can start imagining something that's happening physically, right? So whenever I write y equal to f of x, what do you mean by that? Y equal to f of x? Y is dependent on x. So mentally, when you look at that equation, you will think, okay, IC2 is coming because of VB2. But VB2 is same as VB1. But VB1 happens to be the output and IC1 happens to be the input. So what should I write VB1? VB1 is, see here, VB1 is VT log IC1 by IS. So VB is output, IC is input. Then if you cancel the nonlinearity, then IC2 is IC1. This is I copy and this is almost I reference if your beta is large. Are you getting? So many ways of explaining this. Okay. Okay. Consider beta large. Beta large. Find I copy or I not.
Can you? Oh, why are you giving my flex? Because this one comes out. Can move on.
Okay.
Huh?
Press
What is this?
one. Plug it. Pull away.
This game. Mm.
Okay. Q1 is a diode and Q2 is a transistor. Q1 is a diode and Q2 is a transistor. The current flowing through the transistor and the current flowing through the diode both are same, except that beta error. If you neglect that beta error, then both are same. So how do we solve this? This is a diode. 5K, and here VB on is 0.7. If it is 0.7, this node is also at 0.7. 0.7 volts, right? This is 0.7 with respect to ground. Here also 0.7. So what is the current I? This current I and I naught both are same. So what is I naught? I naught is going to be 10 minus 0.7 by 5K. 5K, right? 1.86 milliampere. 1.86 milliampere. So this is the current I naught. I naught and I reference both are same. Both are same. This current I and I naught both are same. All right. This is a current mirror. So to calculate the biasing current, we just take 0.7 volts there and 10 minus 0.7. That's all. Otherwise, in voltage divider bias, it's a big headache, is it not? VTH, RTH, and all that. Here, nothing is there. Take 0.7 volts, connect a resistor. Because see, when you want to calculate current, there should be a resistor and voltage. Yes or no? So you have to apply Ohm's law. I equal to V1 minus V2 by R. What about problem 2? This is 5 volt. You want to find some reference current here. There is 0.7 volts here. VB on is 0.7. If this node is minus 5 with respect to ground, what if you go up? If you go up, then you have to add 0.7. Am I right? Here, there is minus 5 volts. There is a 0.7 volts drop. So if you go up, it is minus 5 plus 0.7. It is going to be minus 4.3 volt. It's going to be minus 4.3 with respect to ground. So this is minus 5. If you go up here, it is minus 4.3. Am I right? The same minus 4.3 will appear here. So what is the current I? The current I is going to be 5 minus of minus 4.3 by 1K. It is going to be 9.3 milliampere. So this is I naught. This is going to be I naught. So I naught and I reference both are same if beta is large. Beta is large. So this is a simple way of calculating the biasing current. Now just above this Q2, you can connect whatever amplifiers that you want. You can connect a differential amplifier. Multiple differential amplifiers you can connect in parallel. And just switch on one diode and all the devices will get 0.7, 0.7, 0.7 volts like that. Right? So the current, what is the current I here? The current I is going to be 5 minus of minus 4.3. What is I? It is 5 minus of minus 4.3 volts. 4.3 volts by 1K. It is 9.3 milliampere current, right? 9.3 milliampere. So this I is same as I naught. Now, I told you in a differential amplifier, this point P is at virtual ground. This point P is at virtual ground. The gain of full circuit is equal to the gain of half. So you can take half. There is a common emitter amplifier. Minus GMRC is the gain. But for biasing this, we need a current source here. And that current source is this current mirror. This current mirror. So this current source, now we have to do DC analysis for this. DC analysis. The upper portion is only for AC analysis. The upper portion is for AC analysis. Am I right? So the lower portion is for DC analysis. So tell me, what is the DC current? This current I naught and this current I naught both are same. Am I right? This is I naught. This is also I naught. So DC. DC analysis is this. This I know. So tell me, what is DC analysis? We have not calculated anything. The same thing I have drawn here. So this is minus 0.7. This 0.7 volts drop here. Minus 10.7. So what is the voltage at this point? If you go up, you have to add. So this is going to be minus 10 plus 0.7. It is minus 9.3. It is minus 9. So what is I naught? I naught is going to be 10 minus of minus 9.3 by 10K. It is 1.93 milliampere. So this completes the DC analysis. The DC analysis, this completes the DC analysis. All right. You have minus 10. If you go up, minus 10 plus 0.7, minus 9.3 by 10K. 10 minus of minus 9.3 by 10K. Is it not? Or if you want, you can write KVL also. If you want, you can write KVL, or you can write KVL. What is KVL? Here I am having a diode, and here there is minus 10, minus plus 10 volt. And what is this voltage here? This voltage is 10 volt with respect to ground. 1K, 0.7. So 10 volt, is it 1K or 10K? 10K. 10K. So you can apply KVL round the loop. Minus 10 plus I into 10K plus 0.7 minus 10 equal to 0. I equal to 20 minus 0.7. 20 minus 0.7 is 19.3 by 10K. 1.93 milliampere. So this is by KVL. KVL means you have to have loops. Otherwise, simple logic is this node is at minus 10, you go up minus 9.3. 10 minus of minus 9.3 by 10K is 1.93 milliampere. So this completes the DC analysis. So once you know I naught, then what is IC/DC? What is IC/DC? It is I naught by 2. 1.93 milliampere by 2. So this is going to be 2 9s are 18, 6 are 12, 0.965 milliampere. What is GM? It is IC by VT. 0.965 milli by 25 millivolt. 0.965 by 25. It is GM. All right. Okay. It's all DC analysis. Simple. Now, what is AC analysis? AC. AC analysis, I told you, gain of half circuit is equal to gain of full. What is gain of half here? Only 3K and the BJT. So this is what analysis? DC is over. This is AC analysis. So now tell me, what is V0 by V? It is going to be minus GM into RC. Minus 0.965 by 25 into 3K. So this is 3000 by 25, approximately. How much? 120, yeah? What is this value? 0.965 by 25. 115.8. So you can check the calculation, right? 115.8 in the comment section. So nothing is there, is it not? See here, 1, 2, 3, 4, 4 transistor circuit. Orally you can do, right? You want I naught minus 10 here, minus 9.3, minus 10 plus 0.7, minus 9.3. 10 minus of minus 9.3 by 10K, 1.93 milliampere. So DC analysis is over. No voltage divider, nothing. Diode current, you know, DC analysis is over. Then 1.93 by 2 is IC/DC. So now you can go for AC analysis, minus GM into RC. Minus GM into RC. What is GM? IC by VT into 3K. So that ends the voltage gain, right? Okay. Now, two errors are there in the basic current mirror. A basic current mirror is a diode connected to transistor, right? One is the 2 by beta error. That error is 2% for a beta equal to 100, right? We have to decrease the error. The second problem is early effect. Early effect, right? I told you early effect can be removed if you pile up transistors one above the other. That is some sort of a cascade connection, is it not? And there's an engineer called Wilson. I told you he had $100 bet with his friend, right? And anybody who designs a current source or a current mirror with 3 transistors will win that bet. He was working for Tektronix, and you know Tektronix is a world leader in oscilloscopes, right? So those guy, he had a bet with his friend, and then next day morning he came out with a new design, right? So the design is like this: Wilson's current source. But just because Wilson improved Widlar, don't think he's any great than Widlar, right? Widlar is genius. He has given so many design nuggets and nuggets and nuggets of design. Widlar and Talbot, these are 2 friends. They were working for Fairchild, and all the 741 op-amp series is there, no? So they were instrumental in designing so many ICs. So this guy is a genius, but he died at a very early age because he was alcoholic. So let us draw Wilson's current source. So here there is I reference and I copy. Okay, so let's start. Tell me. Step 1. Step 1, IC. Excuse me. Step 1, IC. Step 2 is IC by beta. Step 3 is IC by beta because both have the same VB. Step 4, 2 IC by beta. Step 5, if this is IC by beta, this is IC. Step 6, IC into 1 plus 2 by beta. Okay, that was too fast. We will do once again. Tell me who is the first step. First step is IC. Am I right? Second step is IC by beta. Third step, IC by beta. Fourth step, 2 IC by beta. Fifth step, IC. Sixth step, IC, the entering current equal to leaving current, IC into 1 plus 2 by beta. Now seventh step is, what is the relationship between emitter current and collector current? If you know emitter current, how do you find collector current? It is beta by beta plus 1 times of I, which is IC into 1 plus 2 by beta. This is the relationship between emitter current and collector current is beta by beta plus 1 times of emitter current. So this is 7. Eighth step, tell me, what is the relation between the collector current and the base current? Collector current and the base current. Base current is collector current divided by beta. This is step 8 you can take. Last step is I reference. So what is step 9? I reference. Tell me. I reference equal to IC plus IC into 1 plus 2 by beta, or beta plus 2 by, what is this? IC into 1 plus 2 by beta. This is IC into beta plus 2 by beta plus 2 by beta square. So what is a I copy? It is IC into beta into beta plus 2 by beta into beta plus 1. Beta into beta plus 1. So let me check here. IC by beta, 2 IC by beta. So this is going to be IC into 1 plus 2 by beta. This divided by beta is the base current, right? And the emitter current is this. Now tell me, any algebraic mistake that I have done? Beta plus 2 by beta, beta into beta plus 1. Here IC into 1 plus IC plus 2 IC by beta. This is beta plus, what is the relation between emitter current and base current? Emitter current is this, base current is this. This is beta plus 1. So this is going to be beta into beta plus 1. How do I know that I made a mistake here? Because denominator is beta into beta plus 1, beta into beta plus 1 should come. Then only they will get cancelled, no? Yes or no? Okay. So what is I reference by I copy, or I copy by I reference? This is going to be, help me, what is there in the numerator of I copy? Beta square plus 2 beta. What is that there in the numerator of I reference? Numerator, beta square plus beta plus 2. Beta square plus 2 beta plus 2. Okay. So from here, I copy is going to be I reference. Now, can I divide numerator and denominator by beta square plus 2 beta? What will I get? I'm going to get 1 plus 2 by beta square plus 2 beta. Now, can you see the error? What was the error in the previous case? In the previous case, we had a 2 by beta. For beta equal to 100, the error was 2%. But now for a beta equal to 100, 100 square is 10,000, 2 by 10,000. So the current error, I can confidently say your I copy is close to I reference. is close to I reference. So advantage, the current error is drastically reduced. The Wilson's current source says that the current error, here I missed beta plus 1 because emitter current is not collector, no? This emitter current and base current is, you have to divide the emitter current by beta plus 1. So it is beta plus 2 by beta into beta plus 1. Okay. So then you got this I reference into 1 by 1 plus 2 by beta square plus 2 beta. Your current error is drastically reduced, right? The second advantage is, you can see here, Q3 is just above Q2. Q3 is just above Q2. And what is VC2? What is VC2 of Q2? When this is a short, VB. So the lower transistor will fix VC. The upper transistor will enjoy now. Is it not? So Q2, Q3 acts as a cascode structure. Q3 acts as a cascode structure. Therefore, its output resistance or output impedance increases. So whenever output resistance increases, what will happen to the slope of the characteristic? So if your R0 is large, R0 is always equal to 1 by slope. So what will happen if R0 or slope equal to 1 by R0? 1 by R0. What happens if R0 increases? Then the slope is going to decrease. The slope decreases, then naturally the early effect you can reduce. So Q3 acts as a cascode, therefore its output resistance increases and early effect reduces. What do you mean by early effect reducing? The dependency of IC on VC will reduce, right? The dependency of IC on VC is going to reduce. So both the advantages you are getting in a cascode structure, So I reference is this, I copy is this. So current error is drastically reduced, and Q3, it acts as a cascode structure to shield the matching between Q1 and Q2. It shields the matching. Now, but still designers, they are unhappy. They say that there is a systematic error in this. What is a systematic error here in this Wilson's current source? It's not an error, systematic error. It's like systematically, if a friend borrows, every month 100 rupees from other friend, systematic, every month he will borrow, he will never return. Friends means we don't return, is it not? Close friend means we will not return what is there. Yes or no? So 100 rupees we'll take. Every month 100 we are taking, for example. Are you getting? Then that error is called what error? Anyhow, this fellow knows systematically every month this fellow will come and borrow. Is it not? So a systematic error is there, right? What is that error? That's a fixed error. It will not increase more than that. It will not decrease more than that. What is that error? If you calculate, see here, a fixed error is there. What is VC1 of Q1? But there is a systematic error. Right? What is the error is? What is VC1? VC1, if you see from here, this is C, this is E, this is VC. From VC here, can you see that there is a diode here? There is one diode, and then there is a 0 volt short, and then there is a diode here. There is a diode. So VC1 equal to VB3 plus VB1, which is 1.4 volt. 1.4 volt. What is VC2? VC2 is going to be the collector to emitter voltage. This is VC1, VC2. Here there is a short, it is VB2, it was only this diode. So they directly C is connected with B. So VC equal to VB, right? VB2. Since VC2 equal to VB2 because of the short here. This is VB2. This VC2. So this is 0.7 volts. See, fixed error. We don't call it error, systematic error. So VC1 operating point. What is an operating point? An operating point means a point is always governed by two things. Suppose I have a point. X comma Y is a point. What is a point on a graph? X comma Y. X is VC1, Y is IC1. Both ICs are almost same. For Q1 transistor, this VC1 is at 1.4 volt for Q1. For Q2, same IC, you'll have same IC, but its VC is at 0.7 volts. But IC is same, right? This IC and this IC are same, right? What is there? Your IC, operating current means IC. But designers say that, no, already Wilson's current source is patented. Tektronix is celebrating, are you getting? Wilson is in the books. But analog engineers, they are getting money. You know what they'll do? Every day they go to office, they keep on seeing the circuit. Yes or no? Can we improve this fellow also? Right? So some engineer would have thought, I will eliminate even this systematic error of 0.7 volts. So that means in the field of analog or any field in engineering, there is a what you call a relentless pursuit to perfection. You keep on trying. Next time you come out with a design, you always improve the previous one, right? First was Widlar. Widlar basic current mirror. It is there in every analog IC. People were celebrating. Wilson said, no, we can improve, right? Widlar. And some analog engineer would have thought, no, we'll improve this fellow also, right? So in that pursuit to perfection, they have included an extra transistor there, but don't worry, right? To eliminate, I'm not going to do all the current calculation. Just observe how that 0.7 will go, right? To eliminate the systematic error. So what they'll do to eliminate that systematic error, already we have a transistor like this. And here we have included an extra, am I right? Now to eliminate it, some analog engineer would have put like this. So this is beauty, isn't it? Because how perfect is this? See here, suppose I want to measure Vx with respect to ground, And where are the diodes? Every diode gives a 0.7. This is 0.7. This is 0.7, right? 0.7, approximately 0.7 here, 0.7 here. Now, can you see that this 0.7 compensates with this 0.7? These two are compensating each other. These two are compensating each other. When these two are compensating each other, then this voltage here should be equal to this. But did I short Q1? I didn't short Q1, but it has to behave as short. There is no, because Kirchhoff's law should be satisfied. What is Vx from here to ground? Vx, you can write Vx equal to VB3 plus, this is VB3 plus VB2. But what is Vx this side? This side, VB4 plus, this is VCB. This is VCB1 plus VB1. Now what is VB plus VB? 1.4 volt equal to VB plus VB 1.4 plus VCB1. So what Kirchhoff's law says? VCB1 should be 0. See, everybody knows that to have the basic current mirror, see here, all of you, when can I have these two circuits exactly matched? I want Q1 to be exactly Q2. When can I have Q1? I want, somebody will say simply, what is, boss, if you put short, then both will be same. Yes or no? But if it is short, will it work as current mirror? No, is it not? This should be a diode, this should be a transistor. Then only it is a current mirror. But these two are perfectly matched only when this voltage is 0, this voltage should also be 0. Q1 should be 0.7, Q2. So in that pursuit to perfection, Some analog engineer, he has beautifully connected like this. So this connection tells that your VCB is 0. Now you tell me what is VC2 and what is VC1. What is VC1? You can apply KVL round this loop, right? VC2 equal to VCB2 plus 0.7. VCB is already 0. VCB is already 0. So it is 0.7 volts, right? This is 0. Now what is VC1? It is VCB1 plus 0.7, but VCB1 is already 0, 0.7. So now some analog engineer has eliminated the Wilson's current mirror, right? The error is called what error? Systematic 0.7 error is there. In the VC, IC is almost same, but in VC there is a systematic error, and that error he has eliminated, right? So once in IES they asked what is VC1. In IES exam they asked what is V. For that you should not do all this nonsense, right? What is VC1? If it is given as a problem, what you will do? Problem. Find VC1. Find VC1. How you will do? Huh? You can do by what I have done orally, or you can apply Kirchhoff's law, right? So this is given VC1. Find VC1. So how will you solve? Here there is how much? 0.7 drop. Here there is 0.7 drop. Here there is 0.7 drop. So now you can have a loop, KVL. So how will you solve this? You have to go like this. Route from ground back to ground. From ground back to ground, like this. You have to go like this. Are you getting? From here to here. What is it? Minus 0.7 plus again minus 0.7. From here to here, or like this. This or this is same, like this you have to go. Right? Minus 0.7, minus 0.7, plus 0.7, plus VC1 equal to 0. So VC1 is also equal to 0.7. This is the answer. So you can apply KVL. Getting? Minus 0.7, plus 0.7, plus VC1. Because this point is this, VC1 equal to 0. So VC1 is 0.7. So if VC1 is 0.7, what is VC2? VC2 of course is also 0.7. Because your VC is same as VB. VC is same as VB. VC2 is VC2 minus VE2 or VB2 minus VE2. It is 0.7, short. So this voltage, the voltage here and this voltage both are same. Okay, so this is about the basic current mirror and how to improve the current mirror in a Wilson's current source. So what do you mean by cascode? Whenever a transistor is connected to cathode of the next stage, whenever a transistor is connected to cathode of the next stage, then it is called cascode. It is called what connection? Cascode. So if you pile up transistors one above the other, then such a connection is called cascode. Find I naught, beta large. Okay. Now, how do we solve this? Here there is a diode which takes a drop of 0.7, and from this node, the diode anode is connected here. There is a short here, and then there is one more diode which takes a drop of 0.7. So how much voltage is here? If this is 0.7 volts, if you go up, it is going to be 1.4. Am I right? So we can draw like this. This diode is this, and from here to here there is a short from here to here, and then there is another diode. So first one diode, then there is a short, and then there is another diode. So anode is connected to 10, cathode to ground. This diode is going to give 0.7 drop. This diode also will give 0.7 drop. Then what is the voltage here? 0.7 plus 0.7 is 1.4. Then this current I is same as I naught, right? It is actually I reference by 1 plus 2 by beta square plus 2 beta. So if beta is 100, 100 square, 10,000, right? It's very, very small. So tell me, what is I naught? I naught or I is same. It is 10 minus 1.4 by 1K. 10 minus 1.4 by 1K. So how much is it? 8.6 milliampere. It is 8.6 milliampere. Okay. Now, here there is VEB of 0.7. So what is 10 minus 0.7 here? This is 9.3 volt, 9.3. All right. So what is the current I? 10 volt, a diode, a resistor, 5K. All right. So this is 0.7. 10 minus 0.7 is 9.3 volt. So what is the current I? I is going to be 9.3 by 5K, 1.86 milli. 1.86 milliampere. Am I right? Now, do you remember PNP current directions? PNP current directions we have already done. No? In a PNP, what is the difference between an NPN transistor and PNP? In a PNP transistor, the emitter will be up. The arrow indicates the emitter terminal, is it not? So this is IE, and this will be IC. This is IC, and this is IB. This is IE, IC. And what is this current here? This current is the base current, which is IC by beta, All right. So these are the current directions in a PNP transistor. So if you remember the current directions, then this is also the basic current mirror. Let's see if this current is IC. This current is IC. Then what is the base current here? IC by beta. Both transistors have the same VEB. So this is also IC by beta. So IC by beta here, IC by beta here. This is going to be 2IC by beta. Then what is I here? It is IC into 1 plus 2 by beta. and what is I naught? It is IC. So is this the same equation we got first circuit? Do you remember? I reference is IC into 1 plus 2 by beta. I copy is IC. Right? Let's see. First circuit. Yeah. Can you see here? Your I copy is IC. I reference by 1 plus 2 by beta. Is it not? So your I reference is IC into 1 plus 2 by beta. Your I copy is IC. So what you will write now? This is a solution here. I naught is IC. I reference equal to IC into 1 plus 2 by beta. All right. So if you divide both the equations, what do you get? I reference by I naught. I reference by I naught is equal to 1 plus 2 by beta. So your I naught is going to be I reference by 1 plus 2 by beta. All right. So same thing we got even in I copy is I reference by 1 plus 2 by beta. So this is a PNP current source. This is what current source? PNP. Of course, the solution is only this, only one diode and a resistor, right? So which is first step here? IC. Second step, IC by beta. Third step, IC by beta. Fourth step, 2IC by beta. Fifth step is this. Sixth you can have. So 1, 2, 3, 4, 5. IC, IC by beta, IC by beta, 2IC by beta, and I naught. Now here we have a diode. And again there is a diode here. So how many diodes? 2 diodes. So 5 volt diode. Then there is a short. There is a short from here to here. And then there is a diode. And here you have 5K minus. So what is the voltage now? Tell me what are the voltages? This is 0.7 drop. 5 minus 0.7 is 4.3. 4.3 minus 0.7. So what is 5 minus 1.4? 3.6. So similarly, there is a 0.7 drop here, 0.7 drop here. So this is 5 minus 1.4 is going to be 3.6 volt. This is I. I is same as I naught. So I naught equal to 3.6 minus of minus 5 by 5K. So 8.6 by 5K. So somebody with a calculator can help me. What is 8.6 by 5K? 8.6 by 5K. Oh, this 10K, I wrote 1K here. Okay. So everything is done. We'll make this 1K. What is 8.6 by 5K? 8.6 by 5K. 1.72 milli. 1.72 milliampere. Okay. Now, current mirror with thermal stability. Current mirror with thermal stability, right? So, which resistor will give you thermal stability? It is an emitter resistor. Am I right? Emitter resistor always gives you thermal stability to the circuit. Am I right? Fine. What if we diffuse? Generally in IC, resistors, fabrication of resistor generally are diffuse resistors, is it not? So they have wide tolerance. We should generally avoid them, but okay. Suppose this is 1K, this is also 1K. I have two resistors, 1K, 1K. Then naturally, if it is a perfect balanced circuit, Q1 is same as Q2, then your I reference will be equal to I naught. Will be equal to I naught. But why did we connect these resistors? These resistors are called RE. This is RE. RE. What is the other name for RE? RE is called emitter resistor or emitter degeneration resistor. Degeneration. What do you mean by degeneration? Negative feedback. What do you mean by regeneration? Positive feedback. Degeneration means negative feedback. Emitter degeneration resistor. R is called emitter degeneration resistor. So what is thermal stability? Once again, if temperature increases, then the leakage currents will increase IC. If IC increases, we know that the resistor drop, IERE, will also increase. Now what happens to VB? VB equal to VB minus VE. VB equal to VB minus VE. It is VB minus IERE. It is IERE. So what happens if your IERE increases? If your IERE increases, then your VB will reduce. If your VB reduces, then what is IC? IC is IS into E power VB by VT. So if your VB reduces, then naturally your IC will reduce. So here IC has increased and IC has reduced. That means what? It will come back to the point where it has started. So it's like the current increases and then decreases. That means it is stable. The current is, there is no runaway problem here. The current will come back to the point where it has started. If IC decreases, then IE will decrease, IERE will decrease. If IERE decreases, VB will increase. If VB increases, your IC will increase. So the increase of IC will always be compensated with decrease. So even if there is any temperature problem, say you have designed that for say 1 milliampere current. If temperature increases, the next iteration it will decrease and increase and decrease. It will come back to the point where it has started, right? That is why emitter resistors are also called what resistors? Emitter resistors are also called what resistors? Emitter degeneration resistors. Emitter degeneration means negative feedback. It is emitter resistor provides negative feedback, and negative feedback is going to provide the stability in a system, thermal stability, right? Now, what happens if these resistors are not of same value? If they are different values, then what will happen? What happens if one is 1K, the other one is 5K? 2K, 5K, like that. What will happen if this is R1 and this is R2? I reference and I copy here. What will happen? I reference and I copy. Now, suppose I have two transistors. One is working at 1 milliampere. The other is working at 5 milliampere, 5 milli. Now, the current has increased 5 times. The current has increased 5 times. If the current has increased 5 times, do you think the voltage will increase by 5 times here? Suppose this is VB1 and this is VB2. If current increases by 5 times, the voltage will not increase by 5 times. It is almost same because it is an exponential characteristic. It is an exponential characteristic. So similarly, if I treat this as VB1 and this as VB2, Q1 and Q2 being, and here you have almost I reference, and this is almost, if beta is large, I copy. So now tell me, what is Vx from here to ground? Vx is VB1 plus I reference into R1. Am I right? VB1 plus I reference into R1. What is the Vx here? It is VB2 plus I copy into R2. Now, because of the imbalance here, R1 is different, R2 is different. So naturally, we might expect that these currents are not same. Why they are not same? Q1, Q2 are same, but R1 and R2 are not equal. So maybe because the VBs are different, right? Slightly different, their IC might slightly change. If they slightly change, but still VB1 and VB2 you can cancel. Is it not? VB1 and VB2 are same. Why VB1 and VB2? One will be 0.7001, another will be 0.7002. So you can cancel. When you cancel, you get a beautiful relation here. What is the relation? Your I copy is going to be, what is your I copy? R2 by R1 times of I reference. So the ratio of currents is the ratio of resistors now. So now it is you can have a different magnification of the mirror. Are you getting in on the mirror? What is the term written on the mirror, right? When you go on a bike or a car, objects in a mirror are, what is that? Objects in a mirror are, what do they say? Objects in a mirror, they appear larger than they see, something like that, right? So similarly, there are different types of mirrors. It's not that you exactly have I copy equal to I reference. Your I copy can be a function of I reference, 2 times of I reference, 3 times of I reference, 4 times of I reference. So it's like a different kind of a mirror, something that magnifies the image, right? So if my R2 is 2K, and my R1 is 1K, right? If my R2 is 2K and R1 is 1K, then what? If R2 is 2K and R1 is 1K, then your I copy is going to be 2 times of I reference, 2 times, yeah. Objects in the mirror are closer than they appear, right? In the comment section, very good. Objects in the mirror are closer than they appear, very good, right? So I forgot this. Fine. See, these are small tidbits. Otherwise, we'll get bored, is it not? Because first of all, I don't see you. You are very far. So this is how we can, relax for some time. Fine. So now you understand, whenever you look at this circuit, you understand that I copy is not exactly equal to I reference, because you made a comment that, right, objects in the mirror are, what is that? Objects in the mirror are, let me copy what you said. They are closer than they appear. Very good. Okay, good. So I copy is R2 by R1 times of I reference, right? Great. So we have two advantages here. One is the factor of magnification. The second factor is, of course, the thermal stability part, right? So you can always expect thermal stability in the circuit, right? So this is a simple get problem. Find I naught. Find I naught, beta large. So what is this? I copy, I reference into R1 is I copy into R2. So what is I copy? I copy is R1 by, oh my God, R1 by R2. Okay, forget about algebra, right? Forget about if a problem is given, how would I do it? R1, R2, who will remember, right? All of you see here, we are neglecting this drop, right? So this drop equal to this drop. So this current is going to be 3 milli and this current is going to be I naught. So what is the best way of writing? 3 milli into 3K is equal to I naught into 5K. Am I right? Because the VBs are almost same. This drop equal to this drop. That's all. So what is I naught? I naught is going to be 9 by 5, right? So how much is that? 9 by 5 milli. So 5 ones are 5. 5 ones are 5. 4 8s are, right? 1.8 milliampere. Right? So forget about R1, R2. What you have to do? Ohm's law. This drop is equal to this drop. This drop is equal to the drop. So 3 into 3 is I naught into 5. 3 3s are 9. 9 by 5, it's 1.8, right? So I stand corrected. I reference into R1 is I copy into R2. So what is I copy? I copy is going to be I reference into R1 by R2. Is into R1 by R2, right? So this is better. I like this than that. I reference into R1 is I copy into R2, right? Okay. So this drop equal to this. So this is a get problem for 2 marks. So there is some factor, right? So there's always a factor, right? Now, if you want more current, then what we can do, we can switch 5K this side and 3K this side. Then what will happen if 5K is here and 3K is here? Then your current is also going to increase more than I reference. Is also going to increase more than I reference, right? Okay, so it's 7 o'clock now. Shall we take a break? Can we go for break? Okay. Now, how to connect? Can you hear me? Can you hear me? Yeah. Now, how to connect transistors in parallel? Current sources or transistors in parallel. How to connect transistors in parallel? How to connect resistors in parallel? How to connect resistors in parallel? You have two resistors, R1 and R2. How do we connect resistors in parallel? Now, both ends should be tied here, right? So this is how we connect resistors in parallel. So here we have to tie them here 2 times, right? Because a resistor has got 2 terminals. 2 terminals are there. So you have to tie them like this. This is how resistors are connected in parallel. But a transistor has got 3 terminals. 3 terminals. So when you tie them, two transistors, you have to tie them at 3 points, right? So how do you tie them at 3 points? So both collectors should be shorted, both emitters should be shorted, and both base terminals should be shorted. So I have 2 transistors. How do I connect them in parallel? Both collectors, both emitters, and both base terminals are shorted. So this is how you connect. 2 transistors are connected in parallel. But the same thing, instead of drawing the whole line like this, they even draw like this. This is also another representation of this type of a connection. Still simple is, you can draw a single transistor and put 2 arrows like this. 2 arrows. So this is also a simple way of representation. Still simple, what we can make? Still simple, you can draw a single transistor and write 2 AE. AE is the emitter area. Generally in VLSI, the ratio of currents is the ratio of emitter areas. So you have more area, then you have more current. So 2 transistors in parallel, what do? They don't have a 2 base, 2 emitter, 2 collector like that. Single transistor, but the emitter base junction area, this area, they will increase. And naturally more charge injection, more current will be there. So you can write 2 AE, or you can put 2 arrows, or you can draw like this, whichever you like, right? In IES papers, we have seen like this kind of a representation in IES papers, right? In some gate papers like this, right? Like this also, right? Anyways, like this also they connect, but they're all same. They're all same. And how do you represent a diode? I told you. How do you represent a diode? I'm having a diode. There are 2 ways of representing a diode. All right. One is with an PNP transistor. The other one is with an NPN. But your VB junction or VEB junction should be forward bias. Your VB junction or VEB junction should be forward bias. So you can draw like this. For PNP, this is for PNP. All pull-up circuits, right, which are connected to VCC in VLSI, whenever you design a circuit, they will be of PNP type, because that is how the transistor will be on. But if you have a negative voltage, with a negative voltage also this diode can be on. So they will connect like this. there is a negative supply, then you can draw like this also, right? Your wish. You can have only NPN, you can have only PNP, or an NPN and PNP, right? But whatever it is a diode. It is a diode. If this is V, this 0.7, this voltage is V minus 0.7, this is 0.7 here. So two ways of drawing a diode, right? One is with NPN, the other one is with PNP. So this is the upper portion is for PNP current mirrors. The lower portion is for NPN current mirrors, right? Now, suppose if I have two differential amplifiers, a differential amplifier needs 2 milliamperes of biasing current, another differential amplifier needs 3 milliamperes of biasing current, another differential amplifier needs 5 milliamps of biasing current, then what we will do? You can have a single diode like this, a single diode, and to this diode, you can steer 1 milliampere of current, 1 milli. If it is 1 milli, then if you have two transistors in parallel, then because the VBs are same, the VB is same, this is VB, this is VB, naturally here also you'll have 1 milli, here there is 1 milli. So by Kirchhoff's law, this is going to be how much? 2 milliampere. Am I right? Suppose if you have three transistors in parallel, then this will be 1 milli, 1 milli, 1 milli, or 3 milli. If you have four transistors in parallel. Now, a single diode is there. Here you can have a differential amplifier, which is biased with 2 milliampere current. And this 2 milli will shift into 1 milli and 1 milli. Yes or no? You can have one more differential amplifier like this. So finally, transistors are biasing transistors, right? The current mirrors are used to bias the differential amplifiers in a very simple fashion. Otherwise, one voltage divider, resistor you have to fabricate, one coupling capacitor, then bypass capacitor, then output capacitor. Nothing is there, just a transistor, right, connected in parallel. And if there are two transistors, you will get 2 milliampere. Three transistors, you will get 3 milliampere. Four transistors, you will get 4 milliampere. If your diode current is 1 milliampere. Are you getting? Right? Find I1 and I2. Beta large. I1 and I2 beta large. If VB on mod VB or VEB, whatever, is 0.7. Okay. Now, how do you solve this? There is a diode here and there is a diode here. If this current is treated as I, what is I? Diode, resistor, diode, minus 10 volts. So what is 10 minus 0.7? This is going to be 9.3 here. Minus 10 plus 0.7, minus 9.3. All right. Or you can do it here. Minus 10 plus 0.7 is going to be minus 9.3. 10 minus 0.7 is going to be 9.3. Then what is current I? I equal to 9.3 minus of minus 9.3 by 10K. It is 1.86 milli. All right. Now, if this is I, if this is current I, if beta is large, you will have I here and you will also have I. What is I plus I? 2I. If this is I, this is I, this is I, there is 3I. Therefore, I1 equal to 2I and I2 equal to 3I. So multiply 1.86 by 2 times. What do you get? 1.86 into 2. 1.86 into 2. One 1.86 into 2. 3.72. And what is I3? I2 is 3.72, 5.58. $3.72 and 5.58. Good. So this method of biasing is simple, and the method of calculation is also simple, not like the voltage divider circuit. Now, how can a current mirror circuit will do the job of a capacitor? Will do the job of a capacitor. What is the job of a capacitor? It is meant to block DC and allow AC. It is meant to block the DC and allow AC, right? So how this current mirror circuit can also do the job of a capacitor is, suppose if you know that you have to block a DC of some voltage, say 7 volts you have to block. You can calculate that 7 volts. Accordingly, you can design the current mirror. If your DC calculation is already done, accordingly you can design the current mirror, and you can have a level shift. That is called a level shifter. It is called a level shifter. It is called what circuit? Level shifter. So how to design this? Find the value of resistance R for to block the DC, right? To block the DC. For a DC level shift of some voltage we can take 7 volts. 7 volts. So that means my V1 minus V2 should be equal to 7 volts. V1 minus V2 should be equal to 7 volts. This is V1, V2. So what should be the value of R? Okay. Now let me repeat the purpose of a capacitor here. Suppose I have a transistor circuit. I have a transistor circuit. Okay. Let me do that in a fresh page. See here, what is the purpose of level shifter? Purpose of level shifter. Suppose you have a transistor circuit. And this transistor circuit has a voltage of 7 plus 0.2 sin omega t. It is got 7 plus 0.2 sin omega t. Out of this, who is DC and who is AC? 7 volt is DC, 0.2 sin omega t is AC. If you put a capacitor here, what the capacitor will do? It is going to charge to 7 volts and you are left with only AC output. Some output you will get 0.2, or maybe there's a voltage division between RC and this RL. So that if you draw AC equivalent, you will understand. But your DC is completely blocked here by the capacitor, 7 volt, right? 7 plus 0.2 sin omega t, you block by the level shifter. Now, we have to design a current mirror circuit in such a fashion that I will give input V1 equal to 7 plus 0.2 sin omega t. But my V2 should only be 0.2 sin omega t. That means, where is that DC blocked? The DC is blocked by the current mirror. So, what is in DC analysis? What is V1 minus V2? So, it is 0 plus this. DC analysis says that 7 minus 0 is 7 volt. So, it is blocking DC, but it has to allow AC. It has to allow AC. So, let's see. This is a problem given in exam. Now, we have to do only DC analysis, right? DC analysis. V1 could be 7 plus 0.2 sin omega t, or V2 should be 0.2 sin omega t, or V1 is 7 volts. V1 is 7 volts. Your V2 should be 0 volts, right? Given V1 is 7 volts, V2 should be 0 volts. That means what is the level shift now? V1 minus V2 should be 7. V1 minus V2 should be 7. V1 is 7. Your V2 should be 0. That is given by the examiner. Now tell me. First, let us calculate the current I, because beta is large. So here there is 0.7 drop. Minus 5. Now if this is minus 5, what is this? Minus 4.3. Minus 4.3. So this is going to be minus 5 plus 0.7. Then what is current I? I equal to 5 minus of minus 4.3 by 10k. 9.3 by 10k. Same thing, 1.86 milli. 9.3 by 10K, 0.93 milli. 0.93 milli. 9.3. It is 9.3 by 10K, right? It is 0.93 milliampere. 0.93 milli. So this current also is 0.93. Now tell me, what is V1 minus V2? V1 minus V2, the difference from here to here is 2 drops are there. There is 0.7 here, 0.7 plus IR. It is 0.7 plus IR is 7 volt, the drop between the 2 points. So it is 0.7 plus 0.93 milli into R. So what is R? R is going to be 6.3 by 0.93 milli. So just tell me, what is 6.3 by 0.93 milli? 6.3 by 0.93 milli. 6.77, huh? 6.77 K. So this is given for 10 marks, I think, IES exam. So let me repeat this. If you want a 7 volt drop, 7 volt level shift from here to here, the DC is already dropped by 0.7. The transistor already drops 0.7. You're left with 6.3 volt. So IR should be 6.3. If IR is 6.3 and you're steering a current of 0.93 milli left side, this side also should be 0.93. So 0.93 into R, 0.93 into R is going to be 6.3. So naturally, what is R? But if you ask me, sir, when a transistor can level shift by 0.7, then we can do by 7 volts also. But how many transistors do you need? I'm giving 7. When you come down, you are at 6.3. Again, I have one more transistor you have to connect. No? Here one more, here one more. Like that, 10 transistors you have to connect. And finally, if you take your V2, or V2 is going to be 0, if there are 10 transistors. So each transistor is going to level shift by how much? 0.7, 0.7, 0.7, 0.7. Are you getting? By the time you reach the output 10 transistors, instead, we are going for a current mirror. We are going for a current mirror here. And the DC drop, the current mirror can give you, the DC drop is 6.3. 6.3, when a current is steered of 0.93 milliampere, 0.93 into R is 6.3. So your R is 6.77 K. If you diffuse a resistor of 6.77 K and steer a current of 0.93, then it will give you 6.3 volt drop. 6.3 plus 0.7 is 7. So you can get a DC level shift of 7 volt, right? Now, how does our common emitter look like? The common emitter in the yesteryears, right? In the 1960s, used to look like this. It used to look like this. And to do DC and AC analysis of this, we have spent so much time. Yes or no? So much time. We have spent almost half an hour we did. First we did DC analysis, then we did AC analysis. Then what is your AV for this? Minus GM into RC. And what is GM? IC by VT into RC. And what is IC? IC you will get from DC analysis, and your IC depends on VCC. Depends on VCC. Now what happens if I design this on a cell phone, on a mobile unit? What will happen? Your VCC keeps on decreasing as as you keep on talking and use the cell phone. Your VCC keeps on draining, and the performance of the amplifier will also change, is it not? So then they felt how to eliminate the capacitors, how to eliminate the capacitors. So this section they eliminated by connecting what supply? negative supply. Right? Then this capacitor they have eliminated if you have two symmetrical circuits. If you have two symmetrical circuits, then you can have virtual short, is it not? When you have virtual short, then you can have virtual short. Then there is no need for you to have this capacitor. And who is this resistor? This is a current mirror. This is a current mirror. Current mirror. And this one is a PNP current mirror. PNP current mirror. But if you take differential measurement, then you don't need this capacitor. But if you take single-ended measurement, some 7 plus 0.2 sin omega t, then you might need a level shifter. A level shifter. So finally, what is that we are having in this voltage divider bias? Only transistor is there, right? The complete army has been removed here. R1, R2 capacitor is gone. RE is gone, current mirror. Then capacitor is not needed. Bypass capacitor is not needed because you are already getting zero potential by virtual ground. PNP current mirror is there. Level shifter is there. So once you design such a circuit, your gain is not going to be GMRC. PNP current mirror means GMR0 you will get, is it not? So how does the common emitter amplifier looks like in the present day world? It looks like this. This is our common emitter. Now, in this common emitter, this is your input where you give. And we took almost half an hour to analyze this circuit. But to analyze this circuit, how many transistors? 1, 2, 3, 4, 5, 6, 7, 8. Can you see 2 arrows I have put? What do you mean by 2 arrows? If this current is I, this current will be 2I, no? Then this 2I is split into I and I. Am I right? What is the beauty of this circuit is, even if VCC changes, what is half circuit for this? Half circuit. The half circuit is, here there is an R0, here there is an R0, here also R0. I will draw half circuit, R0. If there is a symmetry, then what is the gain of this circuit? AV equal to, please, I didn't draw DC analysis, AC analysis. Because for a voltage divider bias, you have to do half an hour, we have done. Here nothing is there, half circuit we have removed, minus GM into R0 parallel with R0. What is R0 parallel with R0? It is minus GM into R0 by 2. R0 by 2. Now all of you, what is GM? GM is IC by VT. And R0 is VA by IC. VA by IC. So what happens when I do AV here? AV, it is IC by VT into VA by IC by 2. Can you see that IC is getting cancelled? The IC is getting cancelled. Your AV for this circuit, AV is simply VA by VT by 2. So if you give this to a designer, what he will do? In mind, he will calculate gain. He will say, "Arey, VA kitna hai? VA 300 volt, VT 25 millivolt, 300 by 25 by 2. That is a gain." So he will not do DC analysis, he will not do AC analysis, and the IC is getting cancelled. So there is no question of what, the operating point calculation, because these are operating point independent. Now, if you design this such a circuit in your cell phone, what will happen? Slowly this VCC will keep on decreasing. As VCC changes, what will happen? IC will change. But the gain is not at all dependent on IC. So such circuits, if you introduce in your what you call cell phone, happily the performance of the circuit will be same. Are you getting? So voltage dividers are not needed if you have a negative supply. This is your RE resistor. This is your RC resistor. Next time somebody gives you 1, 2, 3, 4, 5, 6, 7, 8 transistor circuit. 8 transistor circuit, ask you gain, what you will say? Half circuit is minus GM R0 by 2. GM is IC by VT, R0 is VA by IC. IC cancel, VA by VT by 2. That's all. VA orally you have to tell. This is the common emitter amplifier. So are you getting? So the common emitter has now changed. This is our CE amplifier now. Previously, this was our CE amplifier. Now this is our CE amplifier. And the gain is simply VA by VT by 2. Are you getting? VA 300 volt, VT 25 millivolt by 2. Very simple. 300 by 25 milli, right? Okay. So this is the gain. IC cancel. VA by VT by 2. Now, what about current mirror? Using MOSFET. Current mirror using MOSFET. Now, this is still simple because the gate current is 0. The gate current is 0. There won't be any error. There won't be any error. This is I reference. This is I copy. So VGS1 is equal to VGS2. Therefore, I reference is same as I copy. If two transistors have the same what current? Drain current, it means their gate source voltage should also be same. I reference is simply I copy here, right? But is this a logarithmic device or an exponential? No. The MOSFET is a square law device. It is a square law. And if you short it here, it becomes a square root. BJT is exponential. So if you short these two terminals, it becomes a logarithmic device. Say a log with an exponential. Here, square root with square. Square root with square. So I reference is I copy. Or do you remember the drain current equations we have done? Huh? What is the drain current equation we have done? Tell me. ID equal to mu Cox W by L VGS minus VT whole square by 2. Do you remember this? Yes or no? Right? So for M1 transistor, M1, I reference equal to mu Cox W by L 1 into VGS minus VT whole square by 2, or VGS1 minus VT whole square by 2. What is I copy? It is mu Cox W by L 2 into VGS2 minus VT whole square by 2. So what happens if you divide these two, I reference or I copy by I reference, if you do, what will you get? I copy by I reference W by L2 by W by L1. Am I right? Or see, sometimes I might forget, numerator W by L1, this is a headache. Instead, what is a simple way? The current flowing through a MOSFET divided by its own W by L is equal to the current flowing through another MOSFET divided by its own W by L. So I prefer writing I reference. I reference is in which transistor? M1. So I reference by W by L1, its own W by L1 is equal to I copy is M2 transistor, so its own W by L. But in the first equation here, equation 1, this is a clause only when W by L1 is equal to W by L2. If both are same, you can simply say I reference is I copy. But if W by L's are different, then you can have I reference by W by L1 equal to I copy by W by L2. I copy by W by L2. So if two transistors have the same VGS, right? They are in parallel. If VGS is same, then your I reference and I copy are related with W by L, right? If they are in series, we have done problems, no? If they are in series, currents are same, then the relationship is between VGS and W by L. VGS and W by L. Here they are in parallel. VGS is same. When VGS is same, when both have the same VGS, then the relationship is between current and W by L. Current and W by L. So don't forget the square equation and the square root. What is the square equation here? ID is, what is VGS minus VT? VGS minus VT whole square by 2 equal to what? VGS minus VT whole square by 2 equal to ID by mu Cox W by L. Am I right? So this VGS equal to, what do you get? 2ID by mu Cox W by L plus VT. Am I right? This 2 goes there, and then there's a root here, right? 2, and then there's a root, and then a VT. Right? If ID controls VGS, it is square root. Or if VGS controls ID, it is square. ID equal to mu Cox W by L, VGS minus VT whole square by 2. Are you getting? So these are the equations of MOSFET. But this is important for exam, right? This is important. Important. So whether you write it like this or this, it's one and the same. So if your VGS is output and ID is input, it is a square root. If your VGS, if your ID depends on VGS, then it is square. Find I naught. Find I naught. Say this is having W by L1. This is W by L2. Different W by L, W by L3. Find I naught. Or you can have a PNP. Yeah. PNP also. Okay. Let's solve it. In a series circuit, both currents are same. Am I right? This is ID2. This is ID3. ID2 is same as ID3 because it is in series. Series. Now, what is the relationship between ID2 and ID1 or I reference? I reference by its own W by L is equal to ID2 by its own W by L. Am I right? So from here we got ID2. We got ID2 where ID2 is W by L2 by W by L1 into I reference. This ID2 and ID3 are same. Now what about I naught? I naught by its W by L4 is equal to ID3 by its W by L3. Am I right? So this gives you I naught equal to W by L4 by W by L3 into ID3. But what is ID3? ID3 is ID2. ID3 is same as ID2, which is W by L2. 4 by 3 into 2 by 1. Is it not? 4 by 3 into 2 by 1. Therefore, your I naught is equal to W by L So 4 by 3 into 2 by 1 into I reference. So this is the solution, right? But ID2 is same as ID3. No question of W by L and all that. Because series circuit, two currents are same. And rest else current mirror, you can have the W by L relationship. Now in a level shifter, what about AC? AC, you know it, right? What is there to explain AC? Here, can you see in AC, what is the resistance here? R naught, no? R naught. Here there is R pi and R. So what will happen to AC here? AC signal. Tell me AC. I don't have to explain. There is an R pi. There is your R. What is the R value? R value, how much we got R value here? 6.77K, 6.77. And here there is a BJT with R naught in mega ohm. Mega ohm. Now what happens if you give 0.2 sin omega t here? There are 3 resistors in series. In which resistor drop will be more? In this R pi, which is in kilo ohms, 1K, suppose 1K, 6.67K, 7.77K, 1 mega. So it is almost like you have a voltage divider here, 0.2 sin omega t. This is 7K. This is your R naught, mega ohm. So complete output is going to be 0.2 sin omega t. So don't worry about AC. Your job is only to see the DC level shift. So your AC is going to get passed, right? Okay. Where are we? Current mirror. Yeah. Now, same problem. Let me give some numerical values because in exam, he gives numerical values. 1 milliampere. Find IL. So tell me some W by L values. W by L1 equal to say 2. W by L2 equal to 3 or 4. W by L3 is say 5. W by L4 is 2 is there, 4 is there, 5 is there, 3 we will write. W by L 2, 3, 4, 5, 6 we will write. Some numbers, is it not? Find IL. Find IL. So these type of simple questions they will ask in GATE exam. So now you tell me. Now ID2 and ID3 both are same. Am I right? ID2 equal to ID3. Why they are same? Because they are in series. They are in series. Next, you have ID4. There is ID5 and there is IL. So can we have a KCL there? KCL. ID4 is entering current. ID5 plus IL. Entering current at this node equal to leaving. So what is IL? IL is ID4 minus ID5. ID4 minus ID5. Okay. So these are generally entering current because this one is series, the other one the current divides. So we got some relation. Now we'll go for the current mirror. The current mirror says that suppose if this is ID1, 1 milliampere, ID2 and ID1, they form a mirror. ID2 and ID1 form a mirror. And can you see a parallel connection here? Parallel. ID5 and ID1, ID5 and ID1 also form a mirror. Then ID4 and ID3, ID4 and ID3 also form a mirror. Are you getting? So what is IL? ID4 minus ID5. Now you tell me current mirror equations. ID2 by W by L. W by L is 4 equal to ID1 1 milliampere by 2. Right? Can you see? The current ID2 by its W by L equal to ID1 by its W by L. Right? So from here you get ID2. You get ID2. But ID2 is same as ID3. ID2 is same as ID3. Right? This is equation 1. Now you tell me ID4 and ID3. ID4 divided by its W by L equal to ID3 divided by its own W by L 5. So this is another equation. This is another equation. So from here you get from equation 1 you get ID2 and ID2 is same as ID3. ID2 is same as ID3 and then you get ID4, right? And what is ID5 equation? Tell me. ID5. ID5 divided by its W by L equal to 1 milliampere current mirror divided by its W by L 2. Now you do mathematics, right? Simple mathematics. Orally also you can do. What is ID4? Orally. Tell me what is ID4? 4 by 2. 2 milliampere is ID4, ID2. ID2 is same as ID3. So that is 2 milliampere. 2 milliampere. 2 by 5. 2 by 5 is a 0.4 into 3. 1.2. What is ID4? Tell me. What is ID4? Substitute. What is ID4? What is ID4? Tell me. ID4 is 3 by 5. 3 by 5 ID3. ID5 is 3 milliampere. 6 by 2, 3 milli. What is ID3? 3 by 5 times ID3. ID3 is ID2. ID2 is 3 by 5. ID2 is 4 by 2. 4 by 2, right? Minus 3. So 3 by 5 into 4 by 2. 12 by 10. 12 by 10. 1.2. 1.2 minus 3. 1.2 minus 3. 1.2 minus 3, no? Minus 1.8. Yeah. So the current is not sourcing, it is sinking in the opposite. It is sinking in the opposite direction. So finally your IDL is minus 1.8 milliampere. It is minus 1.8 milliampere. Three by 5 into 4 by 2, right? Okay, whatever it is, right? So this is the answer. Okay. Now similarly, this is a gate problem. Okay, so the W by L1 is 3, W by L2 is 4, W by L4 is 2, 3, 4, 5, 6 is 2, some value 4. So some W by L's I have given, right? This is W by L6. So let me write it here. W by L1 equal to 3, W by L2 equal to 4, W by L3 equal to 6, W by L4 equal to 5, W by L6 equal to 2, W by L7 equal to 4. Okay, now please see here, in the differential amplifier, the gate terminal of M3, the gate terminal of M3 here is at 0, and here he has given VDD. So which experiences more potential difference? Naturally VDD. And moreover, this end is ground, this end is also ground. So the M3 MOSFET is off. So whatever current that is flowing here, it is the same current through this amplifier. So this is I2. What is I2 now? I2 by its W by L is 1 milliampere by 3. So I2 is 4 by 3 milli. Am I right? But the same current should flow through M6 also. This is same as I6. This is same as I6. Why it is same as I6? Because series circuit, the same current has to flow through differential amplifier and the M6 transistor. Now, what is the relationship between I0 and I6 here? I0 and I6. I0 by the W by L equal to I6 by W by L is 2. So this is the answer. Your I0 is going to be 4 by 2, 2 times of I6. Your I0 is going to be 2 times of I6, and I6 is already 4 by 3. 4 by 3. So it is 8 by 3 milli. This 8 by 3 milli is the answer. So there is no need of W by L5, isn't it? I have not given any W by L5 because the complete W by L3 itself is waste. W by L3 itself is not needed because the transistor is off. The transistor is off. There is no need of W by L5 and W by L3. So I0 by 4 is I6 by 2, right? I0 by 4 is I6 by 2. So I0 is 2 times of I6. But I6 is same as I2. And I2 is nothing but, how much is I2? It is 4 by 3. 4 by 3. So 2 into 4 by 3 is 8 by 3 milliampere is the answer. Eight by 3 milliampere is the answer. Find AV equal to V0 by V. Find AV equal to V0 by V given mu Cox W by L is 1 milliampere per volt square. The R0 is equal to 1 mega ohm. This is given by gate examiner. R0 is 1 mega ohm. VT is 1 volt. VT is 1 volt or mod VT is 1 volt. Right? Find AV. Find AV. Find AV. Okay. Now, what configuration is this transistor M1? This one. What configuration? Input is given at the base or gate. Output is taken at collector. So, what configuration is this? This is M1, M2, M3, M4. So, let me draw this separately here. So what is the voltage gain of a common emitter here? It is minus GM into R01 parallel with R02, or minus GM into R0 by 2. R and R are parallel, R0 by 2. But what is R0 given? R0 is already given 1 mega. That's all. What is there? GM we have to find. What is GM? What is GM in a MOSFET? Where GM in a MOSFET is, what is ID in a MOSFET? Do you remember ID equal to mu Cox W by L into VGS minus VT whole square by 2. Am I right? What is GM? GM is nothing but dID by dVGS. dID by dVGS, right? This is a formula, just a formula I'm giving. If you differentiate, you get mu Cox W by L into VGS minus VT. So let me substitute here. What is the substitution? Mu Cox W by L is 1 milli. VGS is 2 minus 1. 2 minus 1, that is 1 milli. 1 milli. Right? So how do I get 2 here? Right? By seeing we can tell 2. See here, there is some voltage X here. There is some voltage X here. So according to Kirchhoff's law, X plus X is 4. X plus X is 4. Why X and X? Because ID3 and ID4 are same. ID3 equal to ID4. When two transistors have the same drain current, their VGS are same. Their VGS. So instead of X, we can write VGS3 plus VGS4. VGS3 plus VGS4 is 4, but VGS3 equal to VGS4. That means it is equal to how much? 2. Because X plus X is 4, X is how much? 2. So if this is 2, this fellow will also be X, no? Why, if this is X, why is this X? Because it's a current mirror. And these two currents are same. So this fellow will also have the same X, because the MOSFETs are all similar. The MOSFETs are all similar. The examiner said MOSFETs are all similar. So your VGS is going to be 2. 2 minus 1. So tell me, what is the answer now? Final answer. Final answer is AV equal to minus GM into R0 by 2. Your GM is mu Cox W by L into VGS minus VT from the DC analysis into R0. R0 is 1 mega ohm by 2. So it is minus 1 milli into 2 minus 1 into 1 mega by 2. 2 minus 1 is 1. 1 mega into 1 milli. How much is 1 mega into 1 milli? 1 kilo. Minus 500. It is going to be minus 500 is the gain, the voltage gain of a common source amplifier. So I repeat, the gain is here. Here the gate current is 0. So you don't have to worry about these current mirror transistors. Only this you have to worry. So when you look at M1 and M2, these two transistors, what configuration is this? This is a common source configuration, common emitter, which is common source here. So what will be the gain of common source? Minus GM into RC parallel with R0. Here R0 and R0 are there, minus GM into R01 parallel with R02. Both transistors have same R0. The examiner mentions R0 is 1 mega ohm, so it is minus GM R0 by 2. But GM is mu Cox W by L VGS minus VT from DC analysis. So VGS is 2, so you just substitute 2 there. It is minus 400. So please, VB equal to 0.7 is only an approximation. You have to take VB equal to 0.7 only when the examiner asks you to take. If the examiner says no, that the transistors are nonlinear, then you are not supposed to take 0.7. You are not supposed to take 0.7. Similarly, in a diode, when you will take VD equal to 0.7, only when the examiner gives. Otherwise, diode equation is ID equal to IS into e power VD by eta VT. Are you getting? Right. So, if the transistors, if BJT and MOSFET are non-linear, if the examiner says non-linear, then what equation you should take? BJT. IC equal to IS into e power VB by VT, you have to take. Are you getting? So what is VB? VB equal to VT log IC by IS. IC by IS. IC by IS. Now you tell me, if two transistors are operating at two different VBs, one transistor is operating at suppose 1 milliampere, the other one at 5 milliampere, then this is IC1 and this is IC2, and you want to know this gap, this is called the band gap. If you want to know the small delta V, this delta VB voltage, this is VB1 and this is VB2. Now, what is the difference between VB1 and VB2? Tell me. From here, VB1, I can write VB1 as VT log IC1 by IS. Am I right? Similarly, VB2 is VT log IC2 by IS. Am I right? Just tell me, what is log A minus log B? Log A minus log, what is log A minus log B? Log A minus log B. Log A, VB1 minus VB2 is nothing but VT log IC1 by IC2. Am I right? Log of A by B. So this is very, very important, sir. This will give you the gap. Suppose some students say, sir, one is 0.701, another one 0.702. How do you calculate that voltage? That voltage is given by VT log IC1 by IC2. It is IC1 by IC2. So what happens if this voltage, if this because of this small factor, we neglected them. We neglected because VB1, VB2 is in addition with something. Are you getting something? Suppose I am having 1,000 rupees plus 5 rupees. What is 1,000 rupees plus 5 rupees? 5 you can neglect. And you can say 1,000 plus 5 rupees is 1,000. But I have only 5 rupees with me. Can you neglect? That is the only thing I have. At least I can go home by bus. Yes or no? Right? So 1,000 rupees plus 5 rupees, you can neglect 5. But only 5 is there, you cannot neglect. Sometimes, if the examiner asks you the small band gap between the two diodes or two transistors, then this equation is very handy. Right? But if this VB1 minus VB2 is added to some other factor, then because of this small voltage difference, you can always neglect it, right? VB1 minus VB2, don't forget. Please repeat this in your mind. Repeat this, repeat it. I can hear you. I can hear you from here. Repeat it. VB1 minus VB2 is VT log IC1 by IC2. Repeat it. VB1 minus VB2 equal to VT log IC1 by IC2. Very, very important. This will tell you the band gap between the two diodes. So these are the three non-linear equations. Three non-linear equations. If it is BJT. For MOSFET, tell me what are non-linear equations for MOSFET. ID equal to K times of VGS minus VT whole square by 2. Where K is mu Cox W by L. Mu Cox W by L. Am I right? So from here, what is VGS? From here, we will take, therefore, VGS minus VT equal to 2ID by K, 2ID by K with a root, right? Or VGS equal to 2ID by K plus VT, where K is mu Cox W by L. So these are very, very important non-linear equations. VB1 minus VB2 is VT log IC1 by IC2. ID is mu C ox W by L, VGS minus VT whole square by 2. VGS is 2 root 2 ID by K plus VT. So these nonlinear equations will be handy if the examiner says the device is nonlinear, right? Now in this problem, suppose if this both are given VDD, both are given some voltage VDD or VDD by 2. If both experience the same potential difference, then what will happen? The current is going to split by the W by L. ID3 plus ID5. We have done the problem also, right? ID3 plus ID5 equal to ID2. But this current by W by L is equal to this current by W by L. Are you getting? So you can, because both VGS are same. This VGS and this VGS will be same. Then you can, the same differential amplifier problem we have done. But here, one is getting off, the other one is getting on. That is why the whole current is steered through ID4 and ID6. Am I right? See, MOSFET that way is very simple as compared with BJT. Now, suppose I want the band gap between the two diodes, right? I have a diode. And this diode current is say 10 milliampere, 10 milli. And I have one more diode here. This diode current is 1 milliampere. But if examiner says VB on 0.7, VB on 0.7, then what we can say? This is 0.7, this voltage is also 0.7, V0 is 0. But if he says the transistors are non-linear, with IC equal to IS into E power VB by VT, with IC equal to IS into V power VB by VT, and say beta is large, beta large. Find V0. Find V0. So now, suppose this is Q1 and Q2, you have to use the formula. This voltage is VB1, this voltage is VB2. So your V0 is going to be VB1 minus VB2. So your V0 is going to be VB1 minus VB2. With that, you can solve, right? VT also you can take VT. How much is VT in all our problems? 25 millivolt, right? Find V0. BJTs are non-linear. The circuit given is a Widlar's current source. Current source used to bias amplifiers with microampere of current using kilo ohms resistance. So find the value of R. Consider transistors nonlinear. So this is also a gate problem. Just use the formula VB1 minus VB2 equal to VT log IC1 by IC2. Okay, so we have 10 minutes more. Let us solve this, right? We have 10 minutes to solve all these problems. We'll go slowly. What is V naught? V naught is going to be this voltage minus this voltage. It is VB1 minus VB2. So I told you what is VB1 minus VB2? The band gap between the two diodes. It is VT log IC1 by IC2. Am I right? If beta is large, then IB is almost neglected. If IB is neglected, this is also 10 milli only, right? 10 milli. So 25 milli log IC1 is 10 milli by 1 milli. So 25 milli log 10. What is 25 milli log 10? Calculator. What is log 10? ln, right? 25 milli log 10. $57.56. Okay. 57.56 millivolt. See how much small it is, right? Suppose if one voltage is 0.7, what is the other voltage? VB1 minus VB2 is 57.56. If one voltage is at 0.7, the other voltage is at how much? 0.7 plus this value or minus, plus or minus. So 57.56 millivolt is the gap between the two diode drops. So this is neglected for all practical purposes. But suppose you want to use this reference, band gap reference, for building something else, then you might need, you cannot neglect even this small voltage. 57.56, right? The gate problem. VB1 minus VB2 equal to VT log IC1 by IC2. Similarly, this is VB1, here VB2, and the 10th transistor will have VB11. Am I right? So tell me, what is VB1 minus VB2? VB2 is equal to VB3 equal to VB4 up to VB11. Am I right? Because they are all parallel connection. Tell me, what is VB1 minus VB2? V naught equal to VB1 minus VB2. VB1 minus VB2. It is VT log IC1 by IC2. IC1 by IC2. What is IC1 and what is IC2 here? This is IC1. Here you have IC2, but this current is also IC2, no? IC2. How many IC2s are there? 10 IC2 is 1 milliampere. IC1 is 10 milliampere. But 10 times of IC2, IC2 plus IC2 plus IC2 plus IC2, IC2 plus IC2, right? 10 transistors, IC2 is 1 milliampere. So IC2 is going to be 0.1 milli, 0.1 milli. So therefore, it is 25 millivolt log 10 milli by 0.1 milli. What is ln 100? What is ln 100 into 25 milli? ln 100 into 25 milli. ln 100 into 25 milli. Akash, 115.12. 115. Everybody agree? Rohit, Akash, 115.12. Ankit, 115. Yes, now I agree. 115.12 milli. So everybody say that 115.12. Very good. So this is the band gap between the two diodes. This is the band gap between two diodes. Okay. Now, okay, now what is the function of this current source? See, Widlar has given so many current sources, but name they can give to only one, is it not? So when Widlar was working for Fairchild, so many circuits which he designed, they have patented it. But this particular circuit is named after him, right? Is named after him. They called it Widlar's current source, right? Right. So this current source has got huge benefit if you want to bias differential amplifiers with microamps of current. Microamps. See how intelligent this fellow is. If you want microamps, when your voltage is volts, your resistor should be in mega ohm. Yes or no? Suppose I am having a resistor and I want microamps of current, and the voltage here is 5 volt. 5 volt, 6 volt drop like that. What is 5 by 1 micro? 5 by 1 micro. This is going to be 5 mega. This is going to be 5 mega. Mega ohm resistance cannot be fabricated. Mega ohm resistance cannot be fabricated. Then how can I have a kilo ohm but current should be microamp? How can I have a kilo ohm resistor but the current should be microamp? Tell me, is it possible to have kilo ohm when microampere current is flowing, right? It is possible when the drop across this resistor is millivolt. Now, the whole world thought that we cannot have low power VLSI, right? So this fellow has given a path there. He said, we cannot have low power microamps because we cannot fabricate mega ohm. So the whole world thought, okay, mega ohm is not possible, so microampere is not possible. But this fellow very cleverly, he has put a resistor between the two band gaps. Can you see? VB1 is suppose 0.702. VB2 is 0.701. What is 0.702 minus 0.701? It is 0.001 that is going to get dropped here across this resistor. So that fellow nicely has put one resistor in between the two diode drops. Now nicely the current here is going to be microampere. The current here is going to be This is a beautiful idea. Yes or no? Right? He has put only one. Please don't put two resistors. Here R1, here R2 you should not put. Only one resistor, right? He has stuck there. And what is the drop across that resistor? It is VB1 minus VB2. Please see here. Let me derive this here, right? Just now I told you, this is VB1. Am I right? This is VB2. Here you have R. And this current is I0. Tell me what is KVL here? KVL. Minus VB1 plus VB2 plus I0 into R is 0. What is R? It is VB1 minus VB2 by I0. Can you see? What is VB1 minus VB2? The band gap. It is VT log I reference IC1 by IC2, I reference by I0 by I0. This is IC1. So here I reference is 1 milli, I reference. And here your I0 or IC2 is 10 micro. So you can have 25 millivolt log 1 milliampere by 10 micro divided by I0. I0 is how much? 10 micro. So now you can have kilo ohms and still get what? Microampere of current. So how much is this? 25 milli log 1 milliampere by 10 micro and by 10 micro. How much is this? Huh? They are saying 11.5K. 11.5 kilo ohm. Good. So with the help of kilo ohms resistance, we are able to get microamperes of current, right? Okay, all of you. Now tell me, if this is ground, this voltage is 0, am I right? Then what is the current I? I is going to be V in minus 0 by R or V in by R. This I is same as IC. This I is same as IC. Now, tell me nonlinear equation 0 minus V naught is VB. 0 minus V naught is VB or V naught is minus VB. VB is VT log. What is VB? VB is nothing but VT log IC by IS. IC by IS. So it is VT log IC is nothing but V in by RIS. V naught. Now you can see your output is proportional to log of input. Log of input. We will call this as log amplifier. We will call this as what amplifier? Log amplifier. V naught is going to be VT log V in by R into IS. We have got the same log amplifier using a diode. Using what? A diode. Am I right? So now can you see that this end is grounded? Grounded. And this end is already at 0 potential. So what happens when you have a transistor? This end is ground and this end is also 0 potential. This is behaving like a diode only. Am I right? This is a grounded based transistor is behaving like a diode. It is behaving like a diode. This end is also at 0 potential. So collector based junction is reverse bias. So your V naught is proportional to log of V. Now suppose if you want to remove IS, the reverse saturation current, if you hate, sir, I don't want IS, sir, then you can better have this circuit. Here there is VB1, here there is VB2. VB2. And this is a subtractor. This is a subtractor. Do you remember subtractor I have done? If this is Vx and this is Vy, subtractor will give you what value? Vx minus Vy. Do you remember? Subtractor will always give you Vx minus Vy. What is Vx at this point? What is Vx? It is minus VB2. Vx, right? 0 minus Vx is VB2. And 0 minus Vy is VB1. So your Vx is minus VB2, your Vy is going to be minus VB1. So this is again VB1 minus VB2. So again this is VB1 minus VB2. So tell me what is VB1 minus VB2? What is VB1 minus VB2? VB1 minus VB2, tell me what is it? It is VT log IC1 by IC2. That's all. This is the answer. So let me see what is IC1. This is IC1, which is same as this IC1. Op amp draws no current. This is IC2, which is same as this current. Op amp draws no current. So your IC1 is going to be 5 minus 0 by 1K, 5 milli. IC2 is going to be 2 minus 0 by 1K, 2 milli. So 25 millivolt log 5 milli by 2 milli. This is V naught. This is your V naught. Can you see? Your V naught is 25 milli log 5 milli by 2 milli. Are you getting? So VB1 minus VB2 is VT log IC1 by IC2. And the last one, what is V naught here? V naught is going to be minus VGS. What is VGS in the nonlinear equation? What is VGS in the nonlinear equation? Tell me what is VGS? Root 2ID by K plus VT. Root 2ID by K plus VT. So it is root 2 into ID. What is ID here? Virtual short ID. V in by R. Plus, so there's no root here, plus V. This is V naught. So your output is proportional to root of input. Output is proportional to root of input. This is a square root amplifier. Square root amplifier. This is a square root amplifier. So BJT, if you short base and collector, it is a diode. It is a diode. You got a diode equation there, but here this is a square root. So please don't take VB 0.7 if the transistors are what? Non-linear. The transistors are non-linear, you should not take. Are you getting? So what is 25 milli log 2.5? What is 25 milli log 2.5? Some value. Huh? Okay. We'll stop with this. You can take a screenshot. I'll give you each and every frame. You can take a screenshot if you want. Okay, 10 seconds for each. So for every problem, we have used the same equation. VB1 minus VB2, VT log IC1 by IC2, VB1 minus VB2, VT log IC1 by IC2. Okay, so now we can go for question answers.
Hello.
Yes,
Good evening, sir.
good evening.
Sir, 33F. Yes, so this formula that we are applying, so is it applicable to every MOSFETs that are connected to each other?
Yeah. Every
Yeah.
MOSFET which have different W by L. If W by L is same, then both currents are same.
Okay, the same. Can you go to the next page, 34F? 35, sorry. So in this, we are calculating same, right? If
Same
any.
thing. The current divided by W by L is current divided by W by L.
Okay, so we can apply it to M1 and M5 as well if we want to find out.
Yeah. This is a current mirror, no parallel connection. This is the same current mirror. So the current ID2 is ID1 and ID5 is ID1. If the W by Ls are same.
And
This is
so
the
can
current
we go
mirror.
to present day common emitter that we did before 33F, I think 35, 30F. 30F, I think. This one. So how is this half circuit? How did you draw this half circuit
Half
diagram?
circuit is only this portion, no? This Q1 and Q2.
The whole circuit's half circuit is this.
Differential amplifier half circuit is this upper portion.
So
This
how?
is virtual short, no? This point P is at virtual short.
Okay.
This is a differential amplifier. Can you see Q1 and Q3 are differential amplifier?
Yes, sir.
Upper portion is this RC resistor.
So we are calculating this half circuit only for that differential amplifier, not for the other MOSFETs that are present there.
Where is MOSFET here? All are BJT only, no?
Yeah, sorry. This, all other BJTs that
Yeah,
are.
the complete transistors, the lower portion and all this is only for getting current, biasing current. This portion, these transistors are only for DC analysis.
Okay. Insert 27F. So how did we solve that circuit? I didn't understand.
This one.
Yes, sir.
Yeah, here you recognized that there is a diode here?
Yes, sir.
Yes or no? Here there is 10 volt. If you come down, you have to subtract, no? This
Yeah,
portion.
9.3.
9 point. Here there is minus 10. If you go up, you have to add minus 10 plus 9 point plus 0.7 is minus 9.3.
Yes, so there I understood. How are we applying the concept of current mirror here?
They are all parallel connection. If this current is same as this current, then this current is same as this current, then this current is same as this current. They are all same. Current mirrors in parallel. You have drawn here, no? If this is 1 milli, this will, because here this is VB. This also is VB, no? This also is VB. This also is VB. So this VB is applied to all the BJTs here. All the transistors are on, because if VB, if the transistor base emitter junction is forward biased, then naturally the device is on. So this transistor is on, this transistor is on, this transistor is on, this transistor is on, this transistor is on.
So in
They're all
27F, there you wrote 27F. Can you go to 27F?
Yeah.
So this here, this confused me. I2 equals 3I1.
Yeah, I2 is 3I1 only. No, I2 is 3I, not 3I1. 3I.
Okay, that's what
This is I, no?
confused me. How did you calculate?
Yeah, this is 3I, not 3I1. 3I.
Okay,
I1 is
I got
2I.
it.
I2 is 3I. There is no relation between I2 and I1. I2 is different, I1 is different, no? If you want,
Yes,
we can
sir.
frame a relation.
That's
But
what confused me.
I2 is 3 times of I, I1 is 2 times of I.
So
Yeah.
lastly, what are the formulas that we should remember? Because there are so many things going on in here.
Yeah, for here there is no formula here. Only VB1 minus VB2 is there.
So
That
in-
also we can derive.
in the whole session, what are the
Whole session, only one formula. That too, there is no need to remember. VB equal to VT log IC1 by IC, IC1 by IS, no? You
Yes,
write it 2 times, subtract log A by log B.
VB1 minus VB2?
Or if you remember, VB1 minus VB2, it saves time. VT log.
If you remember any other formulas, just apply the logic.
No, only this. Rest else is VB 0.7 means what is there? Just directly you will take that 0.7 and calculate current. No?
Okay.
That is the only formula.
Thank you. It's done. Thank you.
Right.
Hello, good evening, sir.
Yes.
Sir, can you explain the resistance reflection rule, fifth rule for BJT and MOSFET, sir?
Fifth rule. What is the fifth rule?
We are shorting base and collector.
See, base and collector are shorted. Then across the
Diodes.
current source also there is a voltage, no?
Sir, sir, in MOSFET, we are getting 1 by GM parallel with R0, na, sir.
Yeah.
Sir, this R0 means when we are calculating output resistance, na, sir, why you are considering R0?
Because it is shorted, no? Base and collector are shorted. They are coming in parallel.
But in BJT also we are shorted, na, sir, but
Yeah, if you want, you can put R0 there also. R pi parallel with 1 by
R0.
GM parallel with R0 also you can take. Already 1 by GM is very small. Why R0?
Sir, I'm having doubt that, sir, R0 is an output resistance, na, sir, but
Yes,
we are
it's dynamic
calculating
resistance.
input
It's in mega ohm.
yes, sir. But we are calculating input resistance. Why we need to consider R0, sir?
Because the output and input are shorted, no?
Okay, sir. Yes, sir.
The output and input are shorted. When you see from the input, the output and input both are one.
Yes, sir.
Yeah.
Okay, sir.
Any more questions?
Hello.
Yes.
So in differential amplifier, when W by L will be different for both the MOSFET or BJT.
Yeah.
Sorry, for MOSFET, then how we have to deal?
I told you, no, if two differential amplifiers are there, then ID1 by ID2 equal to W by L2 by W. We have done, no? See the previous, when we started MOSFET, see the DC analysis, you will find one differential amplifier with a different W by L for problem. Or you can do there ID1 by W by L1 equal to ID2 by W by L2. But ID1 plus ID2 equal to that I0.
Okay.
Already done. If you want, we can do what is there.
Yes, we have done once.
See here,
Sir,
this one we have already done in the class, right? This is I0. I0 by Kirchhoff's law is ID1 by ID2. Am I right?
yes, sir.
This is equation 1. What is second equation? This is ID1 divided by its own W by L1 equal to ID2 by its own W by L2. That's all. Because its VGS are same.
Sir, we will just substitute it.
Now
Okay.
you have to solve these two equations.
Yes, sir, yes, understood.
Yeah.
Sir, and when RE is connected, then you are saying that it is like it is acting as negative feedback.
Yeah. That was increase, decrease. No, that is a degenerative operation.
So, in when you will teach feedback, then you will show that how this will act as negative feedback.
Yeah. We'll see there. But otherwise also you can draw like this. This is your VB, no? This is your VB. This is your VE voltage. VE is nothing but what? IERE. So if V0 increases, what will happen? If your output, if your IE increases, your IERE, or you can take here IE or IC. If IC increases, your IERE will also increase. If they increase, your VB will decrease, no? If your VB decreases, then the gain will decrease and IC will decrease.
So, and when RE increases, the gain will decrease and the input resistance will increase. Output,
Yeah. If RE increases,
so output resistance will also increase now.
Yes.
Sir, and how will it affect the bandwidth?
how will it affect bandwidth?
Yes, sir.
Bandwidth is something to do with capacitors, no? Tau.
Sir, there was question when RE will increase and there was floor option, bandwidth decreases.
Then RE comes under beta. We don't know what's that. Maybe that's some transconductance amplifier. Then in negative feedback, naturally gain will reduce, bandwidth will increase, no? Maybe they are comparing from with the open loop with the closed loop. Without RE, with RE they are comparing. With RE, the gain will reduce, so bandwidth will increase. Like that, they might say.
Okay.
1 plus A beta times bandwidth will increase in negative feedback. Without feedback, see what we are comparing is more important. Without feedback with feedback.
Sir, I don't know. The question was just like that.
Okay. We'll see negative feedback amplifiers.
Okay.
Right.
Sir, can you go to 33F, sir?
Hello.
Sir, can you go to 33F?
Yeah.
Sir, here, why you are considering I reference, na, sir?
Why you are considering I reference? I reference, I know that is the current source given. I want I naught in terms of I reference. Find I naught, no? Find I naught
I not.
in terms of I reference.
Okay, sir. Sir, for this type of.
Yes. Yes.
Hello,
Yeah.
sir. 8F, sir. 8.
Yeah.
Sir, here you told in reverse bias. Actually, in reverse bias, we open circuit the diode, no, sir.
In reverse bias, we open circuit the diode. Yes.
Here we did the short circuit, no, sir.
Voltage is 0, no? If voltage is 0, then it is in reverse bias.
Sure.
If here the voltage is 0. Acha, you want to pull this diode out, that is a junction voltage, no?
Yes, sir. Yes, sir.
Collector junction should be forward, collector base junction should be reverse.
Yes, sir.
Reverse means what? This voltage and this voltage I am making same. Can you see?
Yes, sir.
If both anode and cathode are same, then what will happen to the diode? It is reverse bias only, no?
Yes, sir.
So how to make anode and cathode same? We have to put a short between the 2 points.
Yes, sir.
Are you getting?
Yes, sir. Got it, sir.
Yeah.
Sir, and 45. Sir, here we have the formula for VB2 minus VB and so on, no, sir. Here only VB.
Only one transistor is there, no?
That also we can use the
Log
formula.
amplifier, basically.
Okay. Okay, sir. Okay, sir.
Yeah.
Hello, good evening, sir.
Yes.
Sir, 15F.
Your name is?
Sagar, sir.
Okay.
Sir, 8th point I didn't get, sir. How we do?
8th point.
Yes, sir.
IB equal to IE by beta plus 1. IE is already, you know, 6th point, no?
Yes, sir.
IC into 1 plus 2 by beta.
Yes, sir.
Then 8th point will be 6th point divided by beta plus 1.
Okay. And the 7th point is...
7th point is beta times of the 8th point.
Beta times of 8th point.
Because that is base current.
Okay.
No?
Okay, sir.
IC is beta IB.
Yes, sir.
Yeah.
Sir, and 25, sir. 25. Sir, this is current mirror problem, right, sir?
Yeah.
Sir, if there is a resistor in at collector side, then there we should consider VB.
Where there is a resistor, emitter resistors are there.
No, sir. If we consider resistor at collector,
That
then
is load, no. IC will never depend on load. In any BJT, your IC is beta IV or IC will depend on VB. IC will never depend on RC, no. Why do you worry?
okay. In this side also, sir,
In any BJT circuit, your IC. Here, yes, diode is there, no. Now, if you put a resistor, it will depend
yes, that only.
because it's a diode.
Yes, sir.
Yeah.
There we need to consider the drop.
Yeah. You are right. Absolutely.
Okay, sir. Sir, and 30F, sir. Sir, here how we calculate VA, sir?
VA, he has to give. Manufacturer has to give early voltage. That 200 volt, 300 volt, 500 volt, he will give for device. That voltage by VT by 2 is the
Then
key.
Here we no need to calculate anything, sir. Then
Nothing is there.
He
VA
will
by
only
VT,
give
you have to
that.
tell. Whenever a common emitter amplifier is given in differential mode, VA by VT, you have to say. You should not do DC analysis, you should not do AC. That is what I told you, no. Analog bottom line is all about intuition. By seeing a circuit, they will tell 8 transistor, 10 transistor circuit, experienced people. But for simple circuits like voltage divider, we have to do procedure, DC analysis, AC analysis, we have to do.
okay, sir. Sir, and one more note, sir, like how transistor is acting as capacitors.
See, capacitor function it will do. It is not like transistor will behave with 2 plates separated by dielectric, like that it will not behave.
Okay.
What is the function of a capacitor? It is to block DC, no?
Yes, sir.
That much DC it will block, level shifter.
Okay. And
Even
sir,
a single transistor will block a DC of 0.7 volts.
yes, sir.
You give at base and take at emitter, no?
Yes, sir.
So it is also behaving like a small capacitor which blocks 0.7. If you want, suppose your capacitor is blocking 7 volts, then you have to put 10 transistors, no? Instead, we are going for a level shifter.
Level shifters. Okay.
Yeah.
Sir, in one problem, level shifter problem, in question only they have given that V1 minus V2 is 7, sir.
Yeah.
Okay.
The
And sir,
examiner will give V1 equal to 7, V2 equal to 0, V1 equal to 8, V2 equal to 0, like that.
okay, sir. And sir, basically VLSI is like as analog is a design subject, VLSI is device subject, sir. Like we will go inside the device.
No, yeah. I mean, it depends on which, where you are working. If you are working in a fab unit, that is different. If you are working at front end, then it is pure digital design, no? If you are working at analog, it is different. If you are working at physical design, then it is more of software job, clicking job.
Okay.
So physical design or digital design verification you are doing, or analog design, or you are working in a fab unit, or you are in a tool making company, Synopsys or Cadence, Mentor Graphic tool making companies are there, no?
Okay, sir.
You are making a VLSI. It all depends on which platform you are working. So many domains are there.
Okay. Like in the gate point of view, I was asking, sir, like
Our job is only analog.
We will study the IC technology and all in this thing, VLSI, right, sir?
Yes, but VLSI is not there, no? Fabrication little was there, it has removed. Present day VLSI means only MOSFET BJT, MOSFET only.
Okay.
So even if you go for any interview VLSI, they will ask digital design and all these MOSFETs.
Okay.
Yeah.
Okay. Thank you, sir.
Okay.
Sir, in this level shift, can you open 28F?
Yeah.
Sir, this is acting as level shifter for which transistor, sir?
For which transistor? See, this 7 volts is here now. It is
Yes, sir.
coming from some other stage. The 7 volts.
Okay.
That voltage it is removing. Tomorrow, in the beginning class beginning, I will draw the whole op amp, a basic op amp. I will show you from where this node comes. Okay.
Okay, so for the below transistor where we have mentioned R0, for that it is acting as level shifter.
No. This R0 is for AC analysis, not DC. DC
No,
is
sir.
DC means 0.7 volts. AC means R pi and R0 we have to write. What is your analysis now? To block DC or to allow AC?
To block DC.
First block DC means don't talk R0. Talk only 0.7 DC currents. Okay.
Yes, sir. We will be blocking DC at V2, right?
We will be blocking DC. The DC drop is between 0.7 and IR. Because 7
Okay.
volts you have given there, no? See, 7 minus 7 is 0. Remember. 7 minus 7 is 0. So I am giving 7 here, I am getting 0. That means another 7 is dropped across 0.7 and IR.
Where we'll be taking output, sir? That's my doubt.
Output is V2. V2 is free
V2.
from DC.
Yes, sir. Sir, one open 37F.
Yeah.
Not this one, sir. Just before one, I guess. In this, sir, M7 and M6 should be shorted, no, sir, to act as current mirror.
See, it depends, no? This current can control this current also.
Okay.
It is a parallel connection, no?
That should current this. That will control this one, no, sir, because
No
first we
problem.
are
It also can control that. Here, this below I0, I might put one more resistor here and another diode here. Can you see I0 here?
Yes, sir.
Here I will put one more resistor and a diode. What is there? This current will come here. So your job is to adjust accordingly the WL. That is what this designer have to do. Here what we are doing, we are calculating, no? We are just making a calculation. What I am saying is, if this current has to control this, what W/L ratio you have to adjust.
Okay, sir.
That also we can do. Are you getting?
Yes, sir. Yes, sir.
Yeah. Accordingly, we have to adjust the WL. Here nothing, we had no adjustment, nothing. Just calculation we are doing. Current divided by WL, the current divided by WL we are doing. We are not designing anything here.
Okay, sir.
Yeah.
Hello, sir. Hello.
Yes.
Hello, sir. Page number 32, sir.
Page number?
32.
Ah.
I think, sir, previous one or next one. 33. Sir, here, this subject. Okay, sir. Sir, this question also. In this, sir, like we have considered for ID3 equal to
ID3 equal to ID2 series.
ID2. Yes, sir. Correct, sir. And for M1, like the two MOSFETs, sir, this I reference should be equal to ID2, right? Because
ID2 with a different WL. WL is different, no? So I reference
sir,
by W/L equal to ID2 by W/L2. Yes, if W/L1 equal to W/L2, then ID2 equal to I reference.
okay. But sir, like for example, we have VGS is same for both the transistors.
Yeah, because the current is not dependent on VGS alone. It is also dependent on mu Cox W/L. That is why I've used an analogy, F equal to MA. F is force, M is mass, A is acceleration. So who is F here? Current ID. Mass is mu Cox W/L. Acceleration is your voltage, VGS.
Okay, okay.
So your current is dependent on mu Cox W/L as well as VGS minus VT. So now VGS, on paper you can do VGS calculation where we have to do. W/L accordingly you can adjust, no? If you want a different value of current.
Okay.
Suppose you want same current here. What you will do? Same current. Same W/L you keep. What is there?
Okay.
Otherwise,
Sir,
in BJT, what we have to do? We have to connect transistors in parallel, no?
Yes, sir.
That is a headache. 1 milliampere, you want 3 transistors you connect in parallel. Here nothing, W by L ratio, you 3 times you make, finished.
Okay, sir. In case of BJT, it will be like in similar way. We can change the beta value, and
No
we can
beta,
have.
the transistor beta and all same. Emitter area you can increase, like W by L
Okay,
here.
okay,
Emitter areas we can increase.
okay, sir. Yeah, yeah, sir. Sir, if like for example, if like 10 such MOSFETs are in parallel, then we have considered 1 ampere each. Like for example, the current is
1
flowing 1 ampere
milliampere,
each.
10 milliampere will come total.
Yeah. For example, in the same circuit, this page only, if the above circuitry is replaced by 10 MOSFETs in parallel, then this ID3 will be 10 milliampere, sir.
That connecting in parallel is nothing but having a more W by L ratio, I'm saying. Having MOSFETs in parallel, you are saying, no?
Yes, sir.
Instead of connecting MOSFET, 10 MOSFETs in parallel, 10 times W by L if you change, that is 10 MOSFET.
Yes, sir.
Yeah.
Okay.
Are you
So
getting?
sir,
You
this
want 10
current,
times current, what you'll do? What is ID2? W by L2 by W by L1. W by L2, you make 10 times of W by L1. Or your M2 is like 10 times 10 MOSFETs in parallel.
okay.
You want 10 times of current. Arey, yaar, this is simple, no? Somebody
sir.
asks you what you'll do. Will you say 10 MOSFETs I should connect in parallel? That is correct. Or you should say W by L change karo. Just change W by L 10 times. That is enough.
Okay. Yeah, sir. In the BJT circuits, we have like n BJTs in parallel. In that case, like the source was providing on the left side, it was providing 10 milliampere. On the right side, we are considering 1 milliampere each in parallel. So,
Yeah.
so from where that much current is coming actually?
From
Sir?
supply only, 10 milliampere. From VCC.
Yeah, but like you are saying from a single diode, like in this current mirror, from a single diode, this all will be on. So all will be 0.7 volt over there. And
All our transistors are like that, no? There is
Yes,
a
sir.
difference between who gives current and who is controlling BJT. Controlling BJT is VB or diode. But the current IC has to come from VCC only.
yes, sir. So my doubt is like this actually when these BJTs are in parallel, there I mean current each is giving 1 milliampere current and the supply is same, sir, 10 volt. Sir, like then this overall current will be very large amount, sir. That's
Yeah,
what
that has
was
to
it.
come from supply only.
Okay, sir, one more problem is there. In one of the problems, I don't remember the page. See. Just a second, sir. Yeah, sir, this C, sir, you have the modern C you told, I think page number 30. 30. Yeah, in this case, sir, this I is flowing in the left side, our current mirror, and this above is, this differential amplifier. Sir, this should also be I, right? How it is 2I, sir?
Here,
I'm not
two
getting
arrows
this.
I have connected down. Can you see?
Yes, sir. Yes, sir.
2 arrows means 2I.
But sir, VB is same for the both below.
Yes, my dear. 2 arrows means 2 transistors in parallel. You have forgotten.
Okay, sir.
2I means, see there, 2 transistors connected in parallel means 2 arrows.
Okay,
3 transistors connected in parallel means 3 arrows you put there.
Okay, I got it, sir. Thank you, sir. That was the doubt, sir. Thank you, sir. Okay.
Hello, sir.
Yes.
16F page number.
What?
16F.
Yeah.
Sir, previous page, 15. Sir, in this I cap equal to I reference also. In next page.
Yeah.
I cap equal to I reference also.
Yes, sir. I copy is I reference. Yes.
How it?
How it is? Take beta 100. 100 square is 10,000, no? What is 1 plus 2 by 10,000?
Okay.
1 plus 2 by 10,000. 2 by 10,000 is 0.0001.
Neglect.
You have to neglect.
For in this current source only, both ICOPY and iReference are.
Yes. In this current mirror, iCopy and iReference are there. iCopy is this one. Can you see here?
Sure.
iReference is this.
Sir, 18F. 18F.
1.8.
1.8. Sir, in this you take Vx equal to VB3 plus VB2. V for right side VCB also. Both.
Left side Vx is what? VBE 4 plus VCB 1 plus VB2. VB1. Yeah, correct. What is your doubt?
Sir, left side VCB2, no, not VCB2.
VCB2, we don't know that voltage, no? It is X, some X you can take. 0.7 plus X plus 0.7. VCB we don't know. Acha, this is called C. This is called C. C stands for collector. This is called B. B stands for base. The voltage between the two is called VCB.
Okay.
Are you getting?
Yes, sir.
Yeah.
హలో గుడ్ ఈవినింగ్ సార్.
Yes.
సార్ అది లెవెల్ షిఫ్టర్ లో డౌట్ ఉండేది సార్. మీరు అంటే ఎక్స్ప్లెయిన్ చేసేటప్పుడు చెప్పారు అందులో ఏసీ గురించి అంటే యూ డోంట్ హ్యావ్ టు వరీ అబౌట్ ఏసీ అని చెప్పారు సార్. అంటే
ఇక్కడ రాసే కదా ఇక్కడ వోల్టేజ్ డివైడర్ కనపడుతుందన్న 7K. సో మీరు ఇచ్చిన సిగ్నల్ ఇక్కడ వెళ్తుంది బేస్ దగ్గరికి. అవుట్పుట్ ఏమో ఇక్కడ తీసుకున్నారు V2. ఇప్పుడు మీకు ఛాలెంజ్ ఏంటి? ఇది మొత్తం సిగ్నల్ ఏదైతే V1 లో ఉందో అది V2 లో అపియర్ అవ్వాలి, అంతే కదా? సో అది అపియర్ అవ్వాలి అంటే ఏం చేయాలి? ఇక్కడ దాని ఈక్వలెంట్ గీసా. ఈ 7K అనేది ఈ ఆర్ పై ఉందా? ఈ ఆర్ ఈ రెండింటి అడిషన్. ఇక్కడ 1 మెగా ఉంది. ఎక్కడ సిరీస్ ఆమ్ లో డ్రాప్ అయిద్దా, షంట్ ఆమ్ లో డ్రాప్ అయిద్దా? బయటకు వచ్చినట్టే కదా, V2కి వెళ్ళిపోయింది. సిరీస్ లో డ్రాప్ అయింది అనుకో ఇంక బయటికి రాదు, మొత్తం ట్రాన్సిస్టర్ తినేసిందని, అంతే కదా?
అందుకే అంటే డీసీ టైం లోని అంటే ఇది R0 తీసుకోమా సార్? అంటే మనం
డీసీ టైం లో అది VC DC, అది DC డ్రాప్. ఏసీలో చేంజ్ ఇన్ VC R0 డైనమిక్ రెసిస్టెన్స్.
సార్ ఇంకోటి అది ఇప్పుడు కెపాసిటర్ ని మనం యూజ్ చేసింది ఫర్ ఎగ్జాంపుల్ మీరు చెప్పారు 2 స్టేజెస్ ఉంటాయి కదా సార్, ఆ 2 స్టేజెస్ లోని వోల్టేజెస్ ని లాక్ చేయడానికి యూజ్ చేసాం కదా సార్.
అది అలా కూడా చేయొచ్చు. ఎక్కడైనా మీరు కెపాసిటర్ పెడితే దాని పొటెన్షియల్ డిఫరెన్స్ ఓపెన్ సర్క్యూటెడ్ వోల్టేజ్ కి ఛార్జ్ అవుతుంది.
అలాగే ఈ లెవెల్ షిఫ్టర్ ని కూడా చేయడానికి మరి లెవెల్ షిఫ్టర్ లో ఇప్పుడు ఆ డ్రాప్ అనేది కరెంట్ మీద డిపెండ్ అవుతుంది కదా సార్?
అలా కాదు, మెయిన్ ఏంటంటే లెవెల్ షిఫ్టర్ రేపు నేను మీకు స్టార్టింగ్ ఫస్ట్ 10 minutes మీరు మిస్ అవ్వద్దు, 10-15 minutes నేను ఒక సర్క్యూట్ గీస్తాను. నేను ఒక 4 స్టేజ్ ఆప్ యాంప్ గీసి ఎంత లెవెల్ షిఫ్టర్ ఉంటే మనకి అవుట్పుట్ 0 వచ్చేటట్టు అడ్జస్ట్ చేయాలి. మనం ప్రాక్టికల్ గా ఉంటది కదా. ఇప్పుడు ఏంటంటే మనము ఏదో మనకి ఎగ్జామ్ పర్పస్ కి మనము ఆ ప్రాబ్లమ్ సాల్వ్ చేసాం, కానీ అది ఎక్కడ పోయి ఫిట్ అవుతుంది అని మనకు తెలియదు కదా. మనం ఎక్కడ దాన్ని ఫిట్ చేద్దాము మొత్తం సెక్షన్ చేసి అవుట్పుట్ 0 వచ్చేటట్టు ట్రై చేస్తే మీకు ఐడియా వస్తుంది. ఓకే,
థ్యాంక్ యూ సార్.
హలో సార్.
yes
22. Sir, in this hello sir.
Yeah, tell me.
Next page 23.
Hello.
Sir, 21. Hello, sir. Hello. Sir, in this, I not equal to 1.86, sir. I reference by 1 plus beta.
How did I get 1.86?
By
Minus 0.7 is 9.3, no?
Hi, sir. Why you solve this? Why you solve I not equal to I reference by 1? Hello, sir. Hello. Hello, sir. Hello, sir.
I guess he's not here. अभी आ जाएंगे sir. I think he got disconnected.
Look at this. Anne.